This conference will now be recorded.
Okay, so this is Resina, Conference Secretariat at Coalesce Research Group LLC, and I will be available for any of your queries or questions throughout the webinar to help you out technically and organize this webinar successfully. Before we start with the sessions, I guess some of you will be new to the GoToMeetings app, so I will just explain you through the GoToMeetings app once again. On the GoToMeetings app and web page, you can find four icons at the bottom of your center of the screen. That is my camera, share, and leave. My click on that to mute or unmute yourself. I request you all to stay muted while our speakers are presenting their research work so that it doesn't cause any disturbance to them. Camera, you can use this button to share or unshare the webcam. If you have the option to share the webcam, you can do it, or it is completely your choice. Third one is share. You can use this button to share your screen. This is the main part. During your presentation, after I call your name from my side, I will be making you the presenter, and only when I give the permission, you will be able to share your screen. So once I make you the presenter, you can click on the screen icon and you will find a pop-up window to share your screen. And the people using the MacBook, so they have to go into their system preferences and need to give access to share their screen, and they have to leave the session and again join from the same link. Then it is going to work to share your screen from the MacBook. And the last one is leave. This is your fourth icon where you can use this button to leave the session. On the top center, you can find four options. You will have a four icons, that is people, chat, notes, and settings. In the chat option, you can chat with me or any other participants. For the settings, you can use this button to check for the settings of your speaker and microphone. And in the notes section, you can write down the notes going through the presentations. Yes. So as mentioned, kindly remain muted during the sessions so that it doesn't cause any disturbance to the presenters. You can ask questions or you can send your questions in the message box too. Well, let's not take much of your time. Finally, I would like to request you to please give a brief introduction about yourself before starting with the session so that we can know about you virtually. And moving on to the session, the first oral presentation of today will be presented by Dr. Zairin Fatima from University of Lucknow, India. And the title of the talk is Preparation of a Novel Nanocomposite and its Properties for Carbon Dioxide Gas Sensing Applications. Hello, Dr. Zairin. Hello. Your voice is not audible to us. Hello, Dr. Zairin. Your voice is not audible. Yeah, the mic is open, but your voice is not audible.
Okay, now you can hear me?
Yeah, yeah.
Hello.
Now it is audible.
Uh,
Yeah, yeah.
now,
It's perfect. Now you are the
hello.
presenter now. I have given you the screen sharing option. Can you please click on the share icon on
Yes,
your screen?
just a moment, ma'am.
Yes, we can able to see your screen.
Okay. Can I start
Perfect.
now?
Yeah, you can. Yes, perfect. Yeah, please start.
Hello everyone, myself Zain Fatma and I have done my PhD from Integral University and my research work from Advanced Glass and Glass Ceramic Research Laboratory, University of Lucknow, India. These are the contents that I'll be discussing today: introduction, experimental technique, results and discussion, conclusions and references. Nanocomposites are highly used materials in material science due to its enhanced properties. Before understanding what a nanocomposite is, we must know what is a composite. Composite material is basically a combination of two or more components having different physical or chemical properties, and when mixed together, they form a new material which has different properties compared to their parent components. If a synthesized composite has at least one dimension of at least one component in less than 100 nanometer, it is known as a nanocomposite. Now, these newly synthesized nanocomposites are highly favored because they have comparatively improved properties. They have low cost, high performance, and higher durability compared to their parent components. There are many synthesis techniques that can be used to prepare a nanocomposite. However, in this present research work, we have made an attempt to prepare a nanocomposite using melt quenching technique. This is a flow chart which explains the experimental process of just a moment. This flowchart explains the experimental procedure of preparation of nanocomposite via melt quenching technique, in which we weigh and mix various oxides, raw materials of oxides, and the mixture is then mixed into a mortar and pestle, and the mixture is then poured into an aluminum crucible and placed onto a melting furnace for at 1400 degrees Celsius. After the melting is done, this melt is poured into a brass mold and pressed with the help of brass plate to remove any residual stress, and and immediately placed into a preheated muffle furnace for about 450 degrees for 3 hours. The final sample is taken out from the furnace and XRD analysis is performed to check the crystalline or amorphous nature of the sample. If the sample is crystalline in nature, that means you have successfully prepared a nanocomposite, and different characterizations are performed to study their different properties. This is the pictorial flow chart for preparation of nanocomposite, and the flow chart clearly shows the different processes as I explained before. Results and discussion. Now the synthesized nanocomposite, the in present study consists of 40% of silicon dioxide, 35% of boric acid, 21% of vanadium pentoxide, and 4% of phosphorus pentoxide. The density of this nanocomposite was calculated to be 2.46 gram per centimeter cube, and molar volume is 35.11 centimeter cube per mole. Now, herein the density of fabricated nanocomposite is comparatively lesser than the parent components like silicon oxide, silicon dioxide, and vanadium pentoxide. This is probably due to this is indicating that there might be a probable chance of presence of pores within the nanocomposite. Now, to check the crystalline nature of the nanocomposite, XRD was performed. The XRD clearly shows distinct sharp peaks confirming the crystalline nature, with major phase formation of hydrogen silicate hydrate along with some secondary phases like vanadium vanadium phosphate silicate and vanadium oxide hydrate. Now to study the structural analysis, uh, FTIR spectra can be seen. Various sharp and broad transmittance peaks can be observed, in which the a broad peak at 1483 per centimeter wave number is correspond is present due to the asymmetric stretching vibrations of BO bonds. Additionally, some OH bond, that is presence of water molecules, can also be seen at 1625 per centimeter, 2360 2362 and 3603 per centimeter wave number. The presence of water molecules within the nanocomposite is probably due to the high hygroscopic nature of phosphorus pentoxide used for glass synthesis. Now, to study the morphology of this nanocomposite, some analysis was performed. In figure A, a very some micrograph can be seen. It shows a very dense, very mixed morphology of different grains present within the nanocomposite. The blue dotted circles clearly shows compact monoclinic hydrogen silicate hydrate nanorods, and figure B is the enlarged image of red dotted square within of figure A. The morphology clearly shows this micrograph clearly shows different porous sites indicated by blue color arrow, and further enlarged image in figure C clearly shows the hydrogen silicate hydrate nanorods present within the nanocomposite. Apart from this morphology, very big tetragonal like crystal grains can be seen within the nanocomposite. These tetragonal grains are probably due to the presence of tetragonal vanadium phosphate silicate present within the nanocomposite, along with some layered plate-like nanoplates present within the nanocomposite, as shown in figure E and F. These plates are probably due to the presence of vanadium monoclinic vanadium oxide hydrate nanoplates, which we will discuss further in this slides. To study the elemental composition present within the nanocomposite, EDS was performed. The EDS analysis clearly shows various presence of various elements within the nanocomposite like boron, oxygen, aluminum, silicon, phosphorus, and vanadium. Herein, as the table suggests, and the graph suggests that the rate percent of oxygen is the highest, that is 62.54%. This is probably due to the use of oxides for synthesis of nanocomposite. Also, a very small amount of impurity of aluminum can be seen in this nanocomposite. This impurity is probably due to the use of aluminum crucible during the synthesis process. Since the some analysis confirmed the presence of pores within the nanocomposite, BET analysis was performed. Figure A shows that absorption desorption isotherm, and the isotherm clearly shows that type 2 isotherm and with H3 hysteresis. The presence of type 2 isotherm further confirms the porous morphology of nanocomposite, and H3 in the, hysteresis confirms that there is a presence of plate-like layered particles, that is E and F. There you can see the plate-like layer particles. This is further confirmed by BET isotherm. Also, to study the pore diameter of nanocomposite, BJH analysis was performed, and the average pore diameter was found to be 11.9 nanometer. Since the nanocomposite is porous in nature, mm, gas sensing was performed, and various parameters like sensor response, response time, recovery time were calculated. In figure A, uh, a gas sensing curve with different concentration, with increasing concentration of CO2, that is carbon dioxide gases, can be seen within the graph, and on increasing the concentration of CO2 in for example, in first graph, on increasing that is at 200 ppm concentration. On increasing the concentration of CO2 inside the chamber, the molecule absorbed by the nanocomposite film thus decreases the current of the film, and when the gas is removed from the chamber, it regains uh, it regains its original position, and thus various and in this process various graphs are plotted, and their required data is tabulated. Now, to study the response time and recovery time of the graph, The sensor response time is defined as the time required by the sensor to attain minimum current when the gas is exposed inside the chamber, whereas the time required by the sensor to come back to its original state is known as recovery time. Herein, at 200 in figure B, at 200 ppm concentration of CO2, the response time is 18 seconds and the recovery time is 19 seconds. In figure C, the response time and recovery time with different concentration increases as the concentration of CO2 is increased. Also, in figure D, the sensor response graph can be seen that as the uh, concentration of CO2 gas is increasing, the sensor response is also increasing. The required values are shown in table. Now, to further back up our research work, a comparative study has been conducted, and the graph shows previous research articles, previous research work compared to this present research work, which clearly shows that the response time, recovery time, and the sensor response of the present research work is uh, excellent compared to many previous research literatures. Also, the temperature is room temperature, so we can conveniently perform this experiment, this gas sensing analysis at room temperatures. Now, these are the conclusions of my research work. Synthesized nanocomposite SP4 was successfully fabricated by a melt quenching technique. The XRD results confirmed the crystallization in the nanocomposite and formation of various crystalline phases. The SEM micrograph indicated the presence of pores, indicating the porous nature of the synthesized nanocomposite. The EDS analysis confirmed the presence of high weight percent of oxygen on the surface of nanocomposite, which is probably due to the use of oxides for synthesis process. This prepared nanocomposite exhibits excellent gas sensing properties and can be used for carbon dioxide gas applications. To further add to it, we are also working on breath analyzers for light and dark applications, which will be further incorporated in this research work. And these are the references that I've used to uh, back up my work. Thank you all for listening, and I would especially like to thank my supervisor, Dr. Chankiram Gautam, for offering me a great support during all my research work, and Miss Lisa Allen for allowing me to speak up in this platform. Thank you all.
Thank you, Dr. Zaidin, for your presentation. So, any questions from anyone? Okay, no questions then. Thank you once again for your presence and presentation.
Thank you, ma'am.
So our next presenter is Dr. Alexandre Nato from CEMMPRE Polytechnic of Lieira, Portugal, and the title of the talk is Extra Production from Hydrazine Monohydride using Noble Metal-Free Nickel WO catalysts. I'm sorry, numerical and experimental evaluation of damage in laminated composite tubes under low speed impacts. Hello, Dr. Alexander.
Hello, I'm here.
Yeah, so I'm going to make you the presenter. Yes. Can you please click on the share icon? Yes, we can
Can you?
able to see your screen. You can open the presentation.
Yes. Can you see the
Yeah,
presentation?
perfect. Yes, you can start
Okay.
presenting.
Thank you very much. Hello, everyone. My name is Alexandre Neto. I'm 24 years old from Leiria, Portugal, and currently in an automotive engineering master's at the Polytechnic University of Leiria. I will now present to you my work on the numerical and experimental evaluation of damage in laminated composite tubes under low-speed impacts. Starting with the index, I will first give you a topic overview, then we will move on to the research motivation and objectives to then introduce the literature review. I will mainly focus on the methodology and especially the results and findings, ending then with the main conclusions. Okay, to contextualize this topic, I believe you all know that composites are very common nowadays, but they can also be very fragile under certain situations where common damages such as delamination, fiber and or matrix cracking can occur, especially under impacts. Impacts such as low velocity, which are very common in service conditions, can cause consequences that are often overlooked due to not being visible to the naked eye. To combat that, there is a need to study energy variations and determine a gradient to better understand such loads. So, what's motivated me to perform this study, you might ask? I wanted to ensure advancements in the correct dimensioning of carbon fiber reinforced polymer structures, also have a great contribution to understanding the effect of low speed impacts, especially to make composites last longer and be stronger. Objectively, I wanted to perform a numerical evaluation of composite tubes under low speed impacts by promoting various impacts with different energy levels to then correlate with the strain results. For the specific layups that will be addressed in this presentation, I will define the energy limit that produces residual damage, perform experimental testing based on numerical testing, and then create a parallelism between residual strength and fatigue life in experimental testing. But please note that only numerical tests will be presented as the experimental data is still under analysis, okay? The full paper will have every result and comparison though. Moving on, as for what other authors have done, one of the differences in my work is that I will use a vertical drop weight test apparatus instead of a drop hammer test, as we can see in figure 2, used by author 1. Other important conclusions by authors are listed here on the right, but I'll be focusing mainly on the following. First, the fact that quasi-isotropic laminates offer better resistance to impacts. Second, the lamination resistance is influenced by tube layup and does not develop between plies with the same orientation, and that certain layups are more appropriate for distinct loads and load types. Well, we will see by the end of the presentation if I've achieved the same results or not. But before going into the methodology, I highlighted 3 main points that I found other studies were missing. First, assessing the effects of invisible induced damage on the tube life cycle. Second, finding energy limits that produce residual deformation on different layups. And third, obtain a classification of the structural integrity of a composite tube under gradient low speed impact tests. Okay, now about the methodology. We will start with the LS-Steiner parameters, which was the software I used, where I used 2 types of mesh elements due to the geometry and thickness of some. For the impactor, I used 001 elastic. For the supports, I used 024. And to model the composites, I used the MAT 54, but the 55 option due to the Tsai-Wu failure criteria that were preferred for this analysis. The consistent units, you can see them. Then I use hourglass 4 for a more realistic contact and default element for 1. On the right, you can see the numerical test apparatus in figure 4, which was based on the ASTM D7136 norm. It's quite a mouthful, but applied to tubular profiles with the drop weight test method securing the tube at each end. One very important detail that you can see in figure 5 is that I modeled the 12 different composite layers individually so that they could be evaluated separately. Okay. So how did I proceed with LS-Steiner testing? Fundamentally, thanks to a trial and error approach until the Tsai-Wu failure criteria limit was met. For this analysis, it made sense to have 3 different energy damage tiers. First, internal damage, where the tube suffered internal invisible damage. Second, an intermediate level, acting as a midterm between both tiers to show the damage evolution. Then third, a visible external damage, where there was apparent visible damage to the outmost layer. In this case, two distinct layups, L1 and L2, will be analyzed here in detail due to having different external layer orientations to promote dissimilar behaviors and examine potential differences. Well, analyzing the table 2 results for tier 1, so the internal damage, it can be seen that for both layups, the energy level that produces invisible internal damage is quite similar. Moving on then to tier 3, the visible external damage, L1 can take more than double the energy than L2 before the visible external damage is apparent, which is a massive difference. Then the tier 2, which is the intermediate level, was just to show the evolution of damage. The results will be analyzed in detail after we go through the experimental approach methodology first. So regarding that, in figure 6, we can see the machine that was used for the experimental testing, the Instron CIST 9340, where the energy, thanks to the relation between kinetic potential energies, velocity, and drop weight height, the proper setup to emulate the numerical testing was obtained by that relation. 5 different tubes manufactured through the roll wrapping method were tested. Why such layups, you might ask? Well, to test and understand potential differences of their influence on impact resistance. Okay, let's dive into the numerical results. And before that, I just want to make clear how they'll be presented. Firstly, on the left, we will always have 2 graphs. The first being impact force times impactor displacement, where the displacement at 0 force means the amount of plastic deformation on the tube in millimeters. The second graph represents the total energy varying with time, where it is the sum of kinetic and internal energy. The plateau energy is plastic, and the difference between the maximum and the plateau energy represents impact elastic energy. In the middle, we'll have the L1 and L2 damage animation, where disappearing elements represent surpassed SAIU criteria values, therefore permanent damage. And finally, on the right, there will be the key findings from the analyzed results. All of this will occur for the 3 damage tiers. Okay, let's dive into the results. Starting with the internal damage tier, we can conclude that by looking at graph 1, L1 suffers lower peak impact force despite higher impact energy, but shows more deformation, as you can see in the x-axis. Then L1 displays less internal damage than L2, as you can see in the animation. Also, that L2 has more internal damage, but less permanent deformation, which is curious. The damage to L2, as you can see also in the animation, is only to the most inboard layer, unlike L1. And finally, L2 retains more elastic energy than L1. Moving on to the intermediate damage tier, we can see that the force displacement graph curves have similar profiles despite different layups and impact energy. That L1 suffers more than double of the impact energy, but it doesn't translate to twice as much plastic deformation. That L1's spiky FD curve near the maximum displacement, as you can see there, between 4 and 4.5 millimeters, is due to the energy dissipation during the heavy impact. And again, that L2 damaged fill elements, as you can see in the animation, are more widely spread despite impact energy being less than half, which is very interesting. Okay. As for the last tier, the visible external damage tier, again, L1's, let's say, spiky force displacement curve near the maximum displacement, now between 6 and 7 millimeters, is due now to the tube hitting the impactor after recuperating elastically, basically the rebound. Another curious thing is that the outermost layer failure in layup 1 occurs only after the rebound, but the L2, the failure in L2 occurs just after the initial contact, which is very interesting. Also, again, repeating itself, the L2 damaged field elements, as you can see in the animation, are more widely spread despite the similar impact energy. And finally, for both L1 and L2 layups, retain the least elastic energy of all tiers. Also, in order to correlate the impact energy level with the strain results, layup 2 was chosen in the state of externally visible damage, where the most energy happens, to showcase the influence of the layer orientation on being subjected to strain in the moment of the most displacement regarding the impactor. Blue means no strain, and red means maximum strain. We can see very clearly similarities between layers with the same orientation regarding the way the strain is distributed. Most notably, the strain evolves in the opposite direction of the fibers, the fourth layer being very, very apparent, as its orientation is minus 45 degrees to the left, and the strain evolves in a plus 45 degree direction to the right, as well as the outermost layer that is on the far right, where the orientation is 0 degrees axial, so in this case vertical, and it suffers quite a lot transversely. So what can we conclude from all this? First, starting with the study points that, let's say, require further attention in the future, I found that MAT55 properties massively influence the outcome of the results, not only affecting impact behavior, but failure criteria limits as well. So it is critical to insert the correct values in the MAT card. Also, meshing posed a significant challenge, during which I discovered that the selection and sizing of elements are pivotal for achieving a reliable, or let's say a reasonably reliable and accurate simulation. However, the limitation imposed by the layer thinness remains a persistent obstacle. But the major takeaways of this study are that, first, tube layer can drastically affect sustained energy absorption and damage as per author number 2. That secondly, L1 displayed less damage in comparable situations, unlike what author 1 said regarding the quasi-isotropic laminates. Third, despite the similar impact energies for each tier, the permanent damage affected practically the same number of layers throughout, but about 6. And let's not forget that invisible damage is still damage, and that may compromise part lifespan. That also, as we've seen in the previous slide, there is a clear relation between fiber orientation and strain distribution, which is opposite. And lastly, the elastic energy's tendency is to decrease with an increase of impact energy. Okay, so that is all. Thank you all very much for your attention, and feel free to ask any questions.
Thank you, Dr. Alexander, for your presentation. So, any questions from anyone? Okay, no questions then. Thank you once again for your presence and presentation.
Thank you very much. Thank you.
Thank you. So our next presenter is Dr. Delia Teresa Sponza from Docus Eylül University, Turkey. And the title of the presentation is H2 production from hydrazine monohydrate using noble metal-free NiWO catalyst. Hello, Dr. Delia. Hello. Hello, Dr. Delia.
Yes, I am going.
Uh, Dr. Delia, yeah, you have a connection. I mean, the speaker problem. It is resounding. Can you please check with your speaker connection and unmute yourself? Hello, Dr. Delia. Your voice is not audible to us. We can able to see your screen. Hello, Dr. Delia. Are you connected with us?
Okay, can you hear me?
I'm sorry, there is a lot of echo from your side. Can you please set that one? There is a lot of echo coming from your speaker. So can you please set that one because it is causing a disturbance?
I am.
No, no. like
Okay, later. Okay, later.
I'm sorry, Dr. Delia, but there is a lots of disturbance coming, so we cannot ignore that because it's really cause a disturbing sound. So in the meanwhile, you can check with that if you need time, or you can join with your phone and present with your system. If you allow us, I can go to the next presentation, and once you are set up with your speakers and sound, then we can continue with your presentation. So yesterday we have one talk left from Dr. I Yes. So yesterday from the day one, we are left with one talk that is from Dr. Farid Mulia from Institute Technology Bandung, Indonesia. And the title of the talk is Strengthening and Grain Refining of Aluminium Alloy 2014 Viscandium Edition. So now he has joined with us. So we can continue with his presentation. Hello, Dr. Farid. Hello, Dr. Farid. Dr. Farid, are you with us?
Yes, yes.
Okay, perfect then. So I have made you the presenter. Can you please click on the share icon on your screen?
Okay. Can you see my screen?
Yes. Please open your presentation.
Okay. Good morning, ladies and gentlemen. First of all, I would like to
Sorry,
thank you
but
for the time.
presentation is not open. We can still see the screen of GoToMeeting. Yes, now the screen is visible. You can make it a full screen and start presenting. Perfect. Yes, please continue.
Okay. Good morning, ladies and gentlemen. First of all, I would like to thank you for the time that has given to me. Today, I will present our research about strengthening and grand refining of aluminum 2014 with Vanadium edition. Our team consists of three people, namely me, Farid Mularatif, Mrs. Yunia Sarah, and Mr. Hussein Ardi. As we know, aluminum is the metal that most widely used in aircraft component. Even though the application of composite continues to increase, until now, aluminum still account for at least 20% of the airframe weight of the aircraft. There are several types of aluminum used in aircraft, but the 700 alloy, together with the 2000 alloy, represent by far the most common aluminum alloys used in aircraft. And one type of aluminum that applied is aluminum 2014. Uh, it is known that the CO2 emission produced by the aviation sector in 2010 were 448 megaton and are predicted to reach 2,700 megaton in 2050. Regarding to that problem, International Civil Aviation Organization has set a target to reduce 50% carbon dioxide emission in 2050 compared to carbon dioxide emission in 2005. One of the efforts that can be made is by developing technology to improve the efficiency of aircraft. Increasing the aircraft efficiency can be done by implementing lightweight design through improving the performance of existing material. One of the elements that is currently being researched a lot to add to aluminum alloys as microalloying element is scandium. Based on previous related research, the addition of scandium to aluminum alloys has a significant effect on microstructure and mechanical properties. Empirically, there is an increase in yield strength of 50 megapascal for 0.1 weight% of scandium added, as can we see in the screen. Besides of that, scandium also has an effect on grain refinement and allows the formation of small aqueous grain rather than the long dendrite during solidification of the aluminum alloy. The following is the phase diagram of aluminum scandium. There are several phases that can form in this alloy, but the modification of aluminum characteristic due to the addition of scandium occurs largely due to the formation of scandium trialuminate phase. During solidification, the formation of primary scandium trialuminate occurs. This phase plays a role in grain refining. Then during homogenization, scandium trialuminate dispersoid is formed that play a role in increasing the recrystallization resistance and strengthening. Besides of that, during the precipitation hardening, scandium trialuminate precipitate is formed that plays a role in increasing that plays a role in strengthening of the alloy. The following are some the effect of the adding of scandium to aluminum alloy. The primary aluminum trialuminate is play a role in grain refining. Then scandium trialuminate dispersoid play a role in improving the recrystallization temperature, and the scandium trialuminate precipitate play a role in strengthening. There are several phases that can be formed if we add scandium to aluminum 2014. There are alpha aluminum asymmetric, theta as the primary strengthener in the aluminum copper alloy, then scandium trialuminate as grain refining and strengthener, and the W phase that gives the negative effect that consume the copper and the scandium for the precipitation of theta phase and scandium trialuminate precipitate during aging process. There are two objectives in this research. First, determine the effect of scandium addition on the microstructure of 2014 aluminum alloy. Then the second is determine the effect of scandium addition on the mechanical properties of 2014 aluminum alloy. So this is the slope diagram of our research. There are two raw materials that we use. There are this alloy aluminum 2014 and master alloy aluminum scandium. The raw material and then test to produce two alloy composition, namely aluminum 2014 and aluminum 2014 with 0.4 weight% scandium. The alloy then characterized in two conditions, namely as gas and as homogeneous. And then characterization that carry out in this research is tensile stress, XRD, semi-DS, optical microscopy, and hot stress. So this is the composition of the raw material, base alloy and the master alloy. This is the parameter of the casing process. Casing begin with the heating the raw material at temperature 710 degrees Celsius for 20 minutes, followed by stirring and degassing with argon gas for 5 minutes. Next, the melt is poured to Y block steel mold. This is the two alloy composition that studied in this research, namely aluminum 20 and 2014 and aluminum 2014 with the addition of 0.4 weight% of scandium. This is the homogenization parameters that we we do in this research. Then the following is the microstructure of SKS alloy. Based on the result of microscope observation, even though the aluminum has been added, there is still a dendrite structure visible in the aluminum 2014 alloy with the addition of scandium. However, there are formation of small aquexid grain in the microstructure, has been seen in the aluminum 2014 alloy with the addition scandium. Uh, the addition of scandium is not able to transform the overall microstructure because the alloy is in hypoeutectic composition. So that the first phase formed during solidification is the alpha aluminum. This is the sample is in the aqueous condition. There is a color gradation which indicates the occurrence of microsegregation. Even though it is not able to transform the microstructure, the addition scandium can reduce the size of secondary dendrite spacing by 22% compared to alloy without the addition of scandium. The secondary dendrite spacing size can be estimated by the diffusion ripening equation. Based on this equation, the faster the solidification time, the smoother the size of the SDAS. Based on the research conducted by Su, the addition of scandium can shorten the solidification time so that SDAS form will be refined. Following are the phase formed in the sample in aqueous condition. Based on the EDS and XRD result, several phases are formed. The gray phase that outline the dendrite time in optical microscope image is the theta phase. This phase has a elongated morphology with rounded end. Meanwhile, the black intermediate phase is formed along the interdendritic region and has eutectic morphology that resembles the Chinese script-like shapes. Is the alpha iron, which is formed because the alloy has a high iron content. Then this is the microstructure image of alloy after homogenization. As can be seen, but alloy shows the aquexid grain. The color gradation also does not appear in the grain formed in both sample, indicating the microsegregation has not occurred again. Microsegregation elimination in as homogeneous sample occurs due to the homogenization causing the segregated element to experience diffusion. Based on EDS and XRD research, several phases are formed. Apart from the alpha aluminum phase, theta phase, and alpha iron phase, in the alloy with the scandium addition, the formation of scandium trialuminate and W phase was detected. The scandium trialuminate peak is formed due to the formation of scandium trialuminate dispersoid. This dispersoid can play a role in providing the pinning effect, which inhibits the grain growth during homogenization, so that the alloy with the addition of scandium has a finer grain size than the alloy without the addition of scandium. The following are the ultimate tensile strength value of the sample in SKS condition. It can be seen that UTS of the alloy significantly improved by the scandium addition. The UTS is enhanced by 147% from 78 megapascal to 192 megapascal with scandium addition. The addition of scandium leads to formation of finer SDAS, which contributes to increasing the strength of the alloy. In addition to final grain structure, the improvement of UTS value of the alloy also occurs because the effect of solid strengthening as a result of scandium addition. Next, the following are the UTS value of the sample in homogeneous condition. It can be seen that UTS of alloy with scandium addition is enhanced by 69% compared to the alloy without the addition of scandium, the strengthening of S-homogeneous alloy with the scandium addition is occurs due to the grain refinement and the formation of scandium trialuminate dispersoid that hinder the dislocation movement. The following are the hardness value of sample in SKS and S homogeneous condition. The data obtained from the hardness test show that there is consistent result with the tensile test data that addition of scandium is increasing the hardness of the alloy. The addition of scandium cause the increase improvement of hardness of 37% in S-case condition as and 35% in S-homogeneous condition. The deviation of hardness value in the S-homogeneous sample is lower than in the S-case sample, indicating a more uniform hardness of the homogeneous sample. More uniform hardness indicates that homogenization reduces the composition segregation in the S-case sample. So this is the summary of the research of our research. First, the scandium addition to aluminum 2014 alloy could prevent the secondary dendrite arm spacing in SK sample and grain size in the S homogeneous sample. And the number two, the addition of scandium to aluminum 2014 alloy cause an increase in ultimate tensile strength and hardness value in SK sample and S homogeneous sample compared to uh, aluminum 2014 alloy without the scandium addition. So thank you for the time.
Thank you. Thank you, Dr. Farid, for your presentation. So, any questions from anyone? Okay, no questions. So, thank you once again for your presence and presentation.
Okay.
So, moving on to next presentation by Dr. Delia. Hello, Dr. Delia. Are you ready with everything now?
Yeah, I think so. Can
Yeah,
you hear
now it is
me?
perfect. Yes, yes. Now the sound is perfect. So,
Okay,
you are the presenter now. Please share your screen.
okay. I have a problem with share. Do you have my?
Yeah, actually, it was
Yes,
visible. Now it has gone.
yes, please.
No, no, it was visible actually, but now it is
I couldn't.
closed.
It's visible now.
No, no, it is not visible. It is closed.
Okay, I am going to share again.
Yeah. Yeah, now it is visible. You can open your presentation.
Yes, but I couldn't open.
Why?
I
You
don't.
need to share the complete window. I think you are sharing only the screen. When it is asking you, you need to share whole window. Then only we can able to see the presentation and you can able to open.
Okay, okay. I couldn't share.
What is showing, like what is the error you are facing?
Yeah, I am going. There is a problem. Why I couldn't find my...
Yeah, can I know the issue? Like now we can able to see the GoToMeeting screen, but not the presentation.
meeting screen. Oh, okay, I am going again.
Hmm.
Okay. Mhm. I am sorry, it's not possible to open my files. I couldn't log in. Not application.
Are you using the MacBook? I think you are using the Windows.
Yes, but I couldn't find.
Exactly what's the error it is showing?
Mm,
Yes, you can minimize this one, the GoToMeeting screen.
yes,
You can minimize the screen,
but
or else click on the presentation in the taskbar.
yes,
I
but
think
I
it's
couldn't
open.
going to my presentation. I couldn't find the file.
Oh. So in that case, you can do one thing. You can send your presentation to Lisa. So she will present the
Okay,
presentation and you can explain from over here.
okay, okay. Thank you. Okay,
Okay. Yeah,
okay,
please send your presentation to her.
okay, okay. I am sharing. Uh, Later, I can now. I have a problem with the email. Uh,
I'm sorry, like,
Later, now I am going to send my presentation with email.
okay.
Later, if you want later, I can present later my presentation.
Okay, no issue. Like you, in the meanwhile, you can send the presentation. I will go with the next talk. Once
Okay,
we
okay,
receive that
thank you.
one, she will inform to you and we can
Okay,
schedule your talk. Okay.
okay, thank you.
Okay, thank you. So we can move to the next presentation by Dr. Shweta from University of Lucknow, India. And the
Yes, ma'am.
title of the talk is Synergetic Effects of Boron Nitride with Waste Zirconia, Evolution of Structural and Mechanical Properties for Instantaneous Fingerprint Detection, Biomedical Applications. So I'm going to make you the presenter.
Okay, ma'am.
Yes. So please share your screen with us. Perfect. Yeah. We can open the presentation.
The presentation is visible.
No, it's your Gmail, it is showing us like your Gmail screen. You need to share the complete window with us, not only the screen.
नहीं हो रहा। Windows. Entire screen. Sure. Okay.
Yes, now we can see your screen. Perfect. Please continue.
A very good morning to everyone. Myself Shweta. I am PhD scholar from University of Lucknow, India. Today is my oral presentation on the topic synergetic effect of boron nitrate with waste zirconia, evaluation of instantaneous fingerprint detection and mechanical property for biomedical applications. These are the outlines of my presentation: introduction, literature review, objectives, methodology, results and analysis, conclusion, acknowledgement and references. Over the last few decades, the field of bioceramic material has rapidly grown for the fabrication of advanced medical implants and devices. However, bacterial infections can be developed in the bone and material interface by the insertion of poor biocompatible implants. And we are using metal alloy are mainly utilized in the human body due to its bioinert behavior and biological system. Metal alloy implants lack required osseointegration property, which further limits its desirable in vivo stability. And it has some negative effects on the body as the metal alloy uh, uh, produce a bad effect on the human health. So there is a demanding need for the fabrication of safe, inert, and stable biocompatible implants. Here we are using zirconia-based implants. Zirconia is the most significant oxide material that reveals excellent properties such as mechanical strength, biocompatible bioinertness, and thermal stability. Zirconia-based nanomaterials were employed in various dental and orthopedic applications for replacement and repair of damaged parts in the human body. These are the various applications up to date of zirconia nanostructures like dental, implant, drug formulation, oral cancer detection, drug delivery, biosensors, orthopedic implants, and many more. Further, moving to the next slide, we are incorporating hexagonal boron nitrate in the zirconia. Hexagonal boron nitrate act as a very versatile material having layered structure which consists of networks of rings bounded by weak van der Waals forces. It is a isoelectronic with a carbon atom and also named as a white graphite. Further, HBN is a temperature resistant, thermal conductivity and non-toxic material. It is chemically inert in nature and eco-friendly material. We are showing two application of zirconia, that is one for the biomedical application and another is for fingerprint detection. A fingerprint imprint act as a very powerful tool for the individual identification due to the presence of unique and immuted rigid patterns. These are the literature reviews which have been published by various researchers as listed. Further, when we move to the objective of this present research work, it is firstly it is synthesis, then characterization, and lastly result and discussion. In the synthesis part, we have fabricated various composites reinforced with HBN, which are synthesized using a solid state reaction method and sintered at 1000 degrees Celsius for the duration of 4 hours. The waste zirconia which we have used is extracted after the milling process of artificial teeth by the Panna Dental Lab, Lucknow, India. And it has a purity of 99.9% and particle size of 255 nanometer. The HPN powder which we have used is purchased from Sigma Eldridge and has purity assay of 98% and particle size of 1 micrometer. The Further, as we have when we have fabricated uh, is shown in the next slide, then we will do the characterization of the fabricated pellets. The characterization which we have done is density, XRD, FTIR, SEM, mechanical stability, and cytotoxicity. And we have also performed the fingerprint detection on the samples. Further, we move to the result and discussion. In the result and discussion part, we have concluded that the fabricated composite signifies a multifunctional material which can explore new ways of utilization of waste zirconia in the field of biological and latent fingerprint detection application. This is the methodology. In the first figure, 1A, we can see the zirconia block before milling. Uh, as I have told earlier, it is purchased from Panna Dental Lab, Lucknow. And further, after the milling, the waste zirconia is seen in the figure 1B. Next, we have powdered the zirconia and we have added HBN powder in a proper ratio by calculating and weighing accurately using a digital weighing machine. Powdered mixture, when they are prepared with 0, 2, 6 and 10 weight percentage of HBN with 100, 98, 94 and 90% of waste zirconia, and we have named it at ZB 0, 2, 6 and 10 respectively. As we can see in figure F and G, the mixed powder had been transformed into pellet using pelletization process. After the pelletization process, the fabricated composite pellet were sintered in the air atmosphere at temperature of 1000 degrees Celsius for duration of 3 hours at a heating rate of 5 degree per minute. And these are named as sintered pellet in the figure G. Further, the green density and sintered density were evaluated of the pellets. Moving to the next slide, these are the result and discussions. We have performed various characterization on the pellets, sintered pellets. The figure 2 show the variation of green and sintered density with increasing mole percentage of HBN. After sintering of pellets, a proper compaction was observed, which result in the increment of the pellet density. As we can see in figure 2, the density of sintered density is more in the sample ZB2. This sample represent ZB2 with increasing mole of HBN, like we have ZB0, ZB2, ZB6 and ZB10. The density of sintered composite decreases after sequential increment in the HBN amount due to lesser density of HBN as compared to the density of zirconia. Density of sintered composite ZB2 is maximum due to densification and compactness of the sample, which is clearly visible from in the figure 2. And the table 1 shows a detailed comparative study on various compositions which have been published by various researchers, its synthesis method, density, surface morphology, compressive strength of the previous published articles. And it is clearly visible from the table 1 that the fabricated nanocomposite has shown the maximum compressive strength of 266 megapascal. Moving to the next result, the XRD patterns is shown in figure 3. In the first figure 3A, we can see the XRD pattern of pure HBN, which is matched with JCPDS card number 340421. Further, in the figure C, the ZB0 sample XRD can be seen. It has two phases, monoclinic zirconia and tetragonal zirconia. We have tetragonal zirconia as major phase and minor phase of monoclinic zirconia can be seen. Further, when we are in the figure C, as the small amount of HBN was added into the waste zirconia, the major and minor phases of ZB2 remains the same, that is tetragonal zirconia and monoclinic zirconia. However, the intensity of all the peaks seem to be enhanced. In the ZB2 sample, the intensity seemed to be enhanced as compared to ZB0, which reflects the existence of dopant. Further, as the content of HBN increases, the major phase of tetragonal zirconia transform into monoclinic ZrO2 for both nanocomposite 6 and ZB6 and ZB10, including a few peaks of HBN were also noticed at different diffraction angle and their corresponding planes as are visualized in figure D and E. A major peak shift towards the lower wave number of 2 theta is also observed, which owing to the change in their lattice parameter due to increasing content of the dopant. Further, the figure 4, we have also performed theoretical simulation on the fabricated composite. This is done by using various software like Match3 Material Project, crystallography open database, Vista software, and these results were compared to the experimental XRD patterns. The simulated XRD of ZB, the first figure in figure 4a, show pure HBN, theoretical result of pure HBN, and in figure B it shows the theoretical XRD of ZB2 sample, which have tetragonal zirconia with a phase percentage of 68.7 and monoclinic zirconia with a phase percentage of 31.3. These results are in good agreement with the experimental results. Further, moving to the next. In figure 5, the XRD patterns of ZB2, ZB6 and ZB10 are shown. When the 2% of HBN is substituted in the ZB0 sample, the monoclinic zirconia dominates tetragonal with phase percentage of 54.9 and 45.1 respectively. Furthermore, on increasing the weight percentage of HBN into the waste zirconia, that is 6% and 10%, the tetragonal phase of zirconia vanished while the monoclinic appeared with 100% phase concentration for both the composite ZB6 and ZB10, which is in an excellent agreement with match reference number are given in the figure 5b and c. Uh, in this slide, this one thing has been missed. These are the molecular structure of hexagonal boron nitrate, tetragonal zirconia, and monoclinic zirconia. Figure 4c depict proper HBN. Here, green spherical balls represent boron, and blue spherical balls represent nitrogen, which are bond with each other. Further, the figure D show the layered structure of tetragonal zirconia, and the layers are interconnected through the central zirconia atom, and oxygen atom are working as a bridging element, and each zirconia atoms are interconnected to 8 oxygen atom which have atomic radii of 1.6 angstrom, which is of zirconia, and 0.74 angstrom of oxygen. These interconnected atoms indicate probable ZrO2 or OZrO bonding. Uh, Further, in the monoclinic zirconia, every zirconia atom is connected to 7 oxygen atoms, and these interactions have comparable potential vibrations as to show tetragonal zirconia. Further, moving to the next slide, in figure 6, FTIR spectra of the synthesized nanocomposite are shown for the 4 compositions. The FTIR spectra reveals various distant transmission peaks which confirm the presence of different type of stretching and bending vibrations mode in all the composite consist of HBN and ZrO2. Here we can visualize various bands, like here it is OH bending vibrations. At this point we can visualize NH vibrations, ZrOH. Various bonds are shown in the figure 6 at various wave numbers. Further, moving to the next result, in figure 7, this is figure 7, SEM micrograph of the nanocomposite ZB0, ZB2, ZB6 and ZB10 is represented at various magnifications, that is low magnification of 10,000 and high magnification of 40,000. All the micrographs show uniform and interconnected grains which specify the polycrystalline nature of the composite. In figure C and D, we can clearly see well interconnected spherical grains which are red spherical structure with blue arrows. Therefore, it might enhance the mechanical strength due to well interconnected grains. Further, by increasing the weight percentage of HBN into weight zirconia, few hexagonal sheets are clearly visible in the figure F, 7F, which are indicated by red dotted lines and yellow arrows. These spherical shaped grains are probably due to, and these spherical red dotted grains are due to monoclinic zirconia, which is in good agreement with the XRD results. From the SEM micrographs, we can conclude that all the composites show agglomerated grains across the surface. However, as the doping of HBN is increased, these agglomerated grains reveal a well-defined spherical grain formation. In the sample ZB2 reveal excellent. In the figure 7C and D, it reveal excellent grain growth of zirconia and nanosheets which interconnect the grain of ZrO2 and hence protect the crack propagation when sufficient load is applied, which result in better mechanical strength. Further, moving to the next characterization, mechanical graph of nanocomposite sample and Young modulus and fracture toughness with increasing mole percentage of HBN. From the graph 8A, we can conclude that ZB2 sample shows the maximum compressive strength, that is of 266 megapascal, and ZB0 is the second highest, having compressive strength of 224. And these are the values for young modulus and fracture toughness of the nanocomposite. From the mechanical, we can conclude that the sample ZB2 have maximum strength and which conclude that it had excellent mechanical properties. Therefore, the mechanical result is in good agreement with density along with SEM micrograph and make it as a compatible material for biomedical. Further, we have also performed stability test on the composite. Two type of stability has been done in various solvents. First, figure 9a shows weight loss in distilled water, sodium chloride, ethanol and methanol, and figure 9b in various concentration of SCl, that is 10, 20, 40 and 60. From the stability graph, it is revealed that from both these graph we can conclude that ZB2 sample have maximum weight loss, that is of 2 milligram and 1.2 milligram. Further, in figure 10, we have performed MTT assay on the sample ZB0 and ZB2 on SIAH, that is cancer cells. The cytotoxicity result conclude that the ZB2 sample is an excellent biocompatible material having IC50 value of 10 microgram per ml, which reveals that ZB2 composite reveal good cell viability as compared with ZB0 sample. Later, the another application of waste zirconia has been done, that is fingerprint detection. We have performed the fingerprint detection on various surfaces, as we can see in the figure 11, that is compact disc, wooden chair, printer, refrigerator, mobile phone, steel tiffin, glass beaker, virtual reality box, aluminum latch, and polarized glass. For figure 11, the powder of zirconia ZB2 sample has been powdered and it was brushed on the imprinted fingerprint, and they were photographed using under room light by using a phone camera. From these fingerprint result, it is a clear evidence that well-resolved rigid pattern were visualized by both the technique of ZB2 samples. And in the figure 12, we have fingerprint of control and fingerprint with blue ink. And the other figure 12, C, D, E, and F are done by wet method, that is 0.5 ml of distilled water is added into 30, 40, 50 and 60 milligram of the ZB2 powder, and they were poured on the fingerprint imprint and they were dried in room temperature, and these results have been obtained. By these all the characterizations, we can conclude the following results. In this research article, HBN reinforced with waste zirconia composites were successfully fabricated using solid-state reaction method. XRD pattern reveal a scientific change in the phase formation from tetragonal to monoclinic zirconia on increasing the reinforcement of HBN. Further, FESM analysis show well interconnected zirconia grains for all composite, and addition of HBN result in the well-defined grain distribution. The mechanical study revealed an improved mechanical performance for ZB2 composite, which might be due to high density, well interconnected grains. Further, the biological test, that is MTT assay studied on HASI cells revealed that adequate cell viability was observed with the ZB2 composite. The another application, that is the developed latent fingerprint on various non-infiltrate substrates were clearly visualized and can be utilized in forensic investigation. These all results comes to a conclusion that HBN reinforced composite signifies a multifunctional material which can explore new ways for utilization of waste zirconia in the field of biological and latent fingerprint detection application. All these waste zirconia block after milling can be fully utilized as a multifunctional material. Acknowledgement. I appreciately acknowledge the CSIR UGC New Delhi for providing SRF fellowship, and I'm also very thankful to my supervisor Dr. Chankiram Gautam and all faculty members for their constant support. I thankfully acknowledge the head Department of Physics and Chemistry for the XRD and FTIR facility at the University of Lucknow. I'm also thankful to all my lab mates for their constant support and help. These are the reference of the performed work. This article has been published in Journal of Mechanical Behavior of Biomedical Material. Thank you. Hello? 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 Is there any questions? Hello?
Hello. I'm sorry, like I am having some technical issue. So thank you, Dr.
Hello?
Shweta, for presentation. So
Thank you,
any
ma'am.
question? Anyone? Okay, no questions, I think. Thank you once again for your presence and presentation.
Thank you, ma'am.
Thank you. So our next presenter is Dr. Ogung Besin Shepra Olubsola from Federal University of Agriculture, Abeokuta, Nigeria. And the title of the talk is Synthesis and Characterization of 3D pose fluorescent dyes using click chemistry and functionalization of novel 3D pose fluorescent dyes with molybdenum oxide, tungsten oxide, nanocomposite for biosensor and anti-counterfeit. Hello, Dr. Ogung Beston. Hello. Hello, doctor. Your voice is not audible.
How many you please?
Yeah, now your voice is audible. Yes. So can you please share your screen with us?
Okay, please.
Mm.
Mm.
Hello. Is there any issue? Okay. It seems that Dr. Shepra is having issue with sharing the presentation. In the meanwhile, we can show the presentation of Dr. Delia. So Dr. Shepra, you can set up your system so that it will work properly after this presentation.
Please.
Okay, I
Because
am
yours,
ready.
okay. So in the we are going to share your presentation.
Thank
Just
you.
a minute. Okay. Yes, Dr. Delia,
Yeah,
this is your
yes.
presentation. So
Thank
you
you
can
very
just let
much.
us know when we have to change the slide so that she will change the slide accordingly.
Thank you very much to you, to organizing committee for inviting me to this great, precious meeting. Good afternoon to all my colleagues. In this study, I will present an energy source, hydrogen, from hydrazine monohydride using noble metal-free nickel tungsten oxygen catalysts. You can go, please. Next slide. Fossil fuels are rapidly becoming exhausted as a result of increased utilization and global dependence on them as the major energy sources. In addition, global warming and environmental disaster caused by greenhouse gas emissions has led to the serious thinking of alternative energy sources. The global interest in developing green energy alternatives has grown in recent years in order to replace non-renewable fossil fuels. As a non-carbon renewable fuel with the potential to be a clean and sustainable alternative, hydrogen gas is gaining interest from scientists and society alike. Due to the fact that only water is produced as a product of hydrogen combustion, and no greenhouse gases are released, hydrogen is described as a clean alternative fuel. In addition to its high energy density, hydrogen also has a big density, which is approximately 2.75 times greater than that of common hydrocarbon fuels. In today's world, 99% of hydrogen is generated by reforming of thermal cracking natural gas, refining petroleum, or refining light oil using system at high temperatures. Next slide, please. Recent chemical hydrogen storage involving hydrolysis of thermolysis of hydrogen-rich materials and spent fuel generation has emerged as a competitive alternative to a high-pressure hydrogen cylinder for vascular and portable applications. Among the hydrogen-rich materials of interest, hydrogen monohydrate is an appealing candidate thanks to its favorable combination of low cost, high hydrogen capacity, good stability under ambient temperatures. In particular, the decomposition reaction of hydrazine yield only gaseous products, which is highly beneficial for design and practical application of hydrogen source systems. Next slide, please. The development of hydrogen monohydrate as a chemical hydrogen storage material requires high active and selective catalysts for promoting hydrogen production and meanwhile suppressing the formation of ammonia. In the past decades, a number of transition metals alloys have been investigated in terms of catalytic properties toward hydrazine monohydrate decomposition. It was found that alloying is a high effective approach for boosting the catalytic performance toward hydrogen production for hydrazine monohydrate. The alloying aspect could be understood from two complementary effects. The geometric and electronic modification of the catalyst surface, the metallic alloys composed of a combination of precious metals like platinum, iridium, and non-precious metals like nickel, cobalt, and iron generally exhibited favorable performance in both activity and hydrogen selectivity. Next slide, please. The catalytic activity of the noble metal-free alloys is typically inferior. For instance, the reaction rates of hydrazine monohydrate decomposition over the representative nickel-based catalysts such as nickel, copper, cerium dioxide, nickel iron, cerium dioxide, nickel copper, nickel oxygen, and cobalt and nickel molybdenum were one or two orders of magnitude lower than those of the nickel platinum and cobalt platinum catalysts. Currently, the less favorable modification affects of non-precious metals compared to noble metals are still poorly understood, but from the perspective of the cost reduction and growth potential, non-precious metal catalysts represent an important direction in the future research for the hydrogen production from hydrazine monohydrate. Next slide, please. Among hydrazine monohydrate decomposition catalysts from the literature all suffered from serious activity loss in cyclic usage. Currently, the mechanistic reasons for the poor stability remain unclear. Possible factors influencing the stability of hydrazine monohydrate decomposition catalysts include particle agglomeration, subtle phase transformation, and strong binding of the products under or intermediate on the catalyst surface. Next slide, please. The aim of the study is the synthesis of the nickel tungsten oxygen derivative nanocatalyst under laboratory condition to produce hydrogen energy from hydrazine monohydrate under reductive annealing condition. The catalyst prepared under optimal condition showed excellent activity, selectivity, and exceptionally high density in catalyzing hydrazine monohydrate to perform hydrogen. The nanocomposite produced under laboratory condition were analyzed by some analyzes like field emission scanning electron microscope, X-ray fluorescence, Browner Emmett-Taylor analysis. Furthermore, the effects of contact time, nanocomposite concentration, power, pH was investigated on hydrogen yields. Next slide, please. Some operational conditions was used to detect the hydrogen production. The noble metal-free nickel tungsten oxygen catalyst concentration was increased. The time was increased. The hydrazine monohydrate concentration was increased. The pH was adjusted to acidic, neutral, and alkaline conditions. And the ratio of nickel to tungsten was investigated on the hydrogen production. Next slide, please. Some chemicals was used to produce the nanocomposites. For example, nickel chloride hexahydride, sodium tungsten dihydride, ethanol, sodium hydroxide, hydrazine monohydrate were used from the commercial offices. Next slide, please. Catalyst was performed under laboratory condition. Sodium vanadate was dissolved in dissolved water. Certain amount of nickel chloride was added. A magnetic stirrer was used to mix the composite. The samples was collected after cooling at ambient temperature. Then distilled water ethanol was added and a vacuum dried at 60 centigrade Celsius was used for 2 hours. The prepared sample was subsequently annealed at 3 different temperatures, 350 to 400 and 600 centigrade degree under following the hydrogen production during 2 hours. Next slide, please. The hydrogen gas was measured using visible light activated photocatalyst hydrogen production. Yes. Next slide, please. XRD analysis was performed. The results showed that nickel tungsten with significant peak broadening and diffuse scattering, indicating the formation of poorly crystallized product. Further annealing the sample at elevated temperature in air could help remove possible solvent residue, improve its crystallinity, promote crystalline growth, and results in a well-defined XRD pattern as mentioned in the literature. Next slide, please. 350 centigrade derece also showed similar XRD pattern to that of hydrothermal sample, but with a new peak appearing at theta equal 35 degree, matching well with the 111 peak of the nickellium tungsten phase. At increasing the annealing temperature to 400 centigrade degree, this peak become intensified with a low angle shift by 0.2 degree, which correspond well to the 211 peak of the nickellium tungsten phase. The diffraction peaks from the nanocomposite sample completely disappeared and were replaced by the characteristic peaks from the tungsten oxide. With further elevation of the annealing temperature to 600 centigrade degree, vanadate oxide with 2 value was reduced to metal tungsten with the nickel tungsten phase still preserved. Next slide, please. Here you see this XRD analyze at 3 different annealing temperature, as I mentioned before. Next slide, please. Futter and Raman analyses were performed to detect the hydrothermal sample properties. Intense peak at 822 per centimeter corresponding to a stretching vibration of oxygen tungsten oxygen. Air bands at around 1650 and 300 4,000 per centimeter should be assigned to the hydroxide bending and stretching vibration of the adsorbed water molecules. Next slide, please. The Raman spectrum clearly showed a strong band at 883 per centimeter, which should be described to the stretching vibrational mode of the terminal tungsten oxygen bonds, consists with the featured assembly of tungsten oxide octohedra in the nickel tungstate structure. Next slide, please. Here you see the Raman analysis and IRI analysis, as I mentioned before. Next slide, please. Team and RTM analysis results was investigated by to detect the diffraction peaks. As you see in the next figure, you will see the said pattern discern to evolutionary reduction of the small nickel tungstate crystallized in the hydrothermal sample during the reductive annealing processes from the initial precipitation of nickellium vanadate to the tungstate to the concurrent formation of nickel vanadate and vanadate oxide, tungstate oxide, and to the metallic nickellium tungsten and tungsten phases. The high resolution TIM images reveal the microstructure and phase constitution of the reduced samples. In the 350 centigrade Celsius reduced sample, the lattice fingers with the interplanar distance of 0.207 and 0.245 nanometer could be assigned to the 111 plane of nickellium vanadate and the 002 plane of nickel tungsten respectively. Please, next slide. Here you see the analysis result as I mentioned before. Next slide, please. The TIM images reveal the microstructure and phase constitution of the reduced samples. In the 350 centigrade degree reduced sample, the lattice fringes with interplanar distance of 0.207 and 0.245 nanometer could be assigned to the 111 plane of nickel tungsten and the 002 plane of nickel tungsten respectively. Next slide, please. Heritem analysis results showed the nickel vanadate and vanadate amorphous phases in the reduced samples. Next slide, please. XPS analysis results showed the surface sensitive properties as presented in next figure. Hydrothermal sample exhibited only nickel-2 and tungsten 6 signals. After the reductive annealing treatment, additional signals of metallic nickel oxide were detected and their intensities increased with increasing annealing temperature. Next slide, please. Here you see the images here. Next slide, please. Now we want to show you some equation with the degradation of hydrogen monohydride to hydrogen with the nanocomposite produced under laboratory conditions. Next slide, please. Some operational conditions were also investigated during this procedure. Next slide, please. Now I want to show you the effect of molar ratio of nickel-2 tungsten on the hydrogen production from hydrazine monohydride. This ratio causes a variation of catalytic properties toward hydrazine monohydride decomposition, and the optimal nickel to tungsten precursor molar ratio was determined to be 1:1. Next slide, please. Here you see the effect of this ratio. At 1:1 ratio, the hydrogen production rate was very high. In the other ratios, the hydrogen production rate decreased. Next slide, please. Now you see the effect of nanocatalyst concentration of hydrogen production. For maximum hydrogen production, 1 milligram per liter nickel tungsten oxygen nanocomposite concentration is very effective. Next slide, please. Here you see the time, effect of time on hydrogen production. The maximum retention time is 30 minutes for maximum hydrogen production. Next slide, please. Effect of pH. At neutral conditions, the hydrogen production is maximum. Next slide, please. The temperature. Reductive annealing temperature exerted significant influence on the catalytic properties of the catalyst. 350 reduced catalyst activity and hydrogen production was 30 mole per liter. Next slide, please. Now you see the effect of temperature at 200 centigrade degree. The maximum hydrogen production yield was detected. Next slide, please. Thank you very much. By the production of this nanocatalyst, hydrogen production was effectively produced from hydrogen monohydrides. Some operational conditions is very important for the and affecting the hydrogen yields. Thank you very much. Yes, I summarize the results. Thank you very much.
Thank you, Dr. Delia, for your presentation.
Thanks a lot.
Thank you. So, moving on to the next presentation by Dr. Shepra. Hello, Dr. Shepra, are you ready with that? So, we received your presentation. Now, Lisa will share the screen. If you are ready, then we can start.
I'm ready, please.
Okay, perfect. Then,
Distinguished scholars, my name is Shifra Olubusola Ogungbeso. I'm a PhD student of Southeast University from Nigeria. I'll be presenting on synthesis and characterization of 3D POSS fluorescence dye using click chemistry and functionalization of novel 3D POSS fluorescence dye with molybdenum oxide tungsten oxide nano hybrid film. The outline: introduction, justification, broad objective methodology, results and discussion, conclusion. Introduction. Human corruption and criminal activities globally are some challenges affecting the protection, conservation, management, and enhancement of the environmental resources around us. We have traditional anti-counterfeiting detection method in place. However, there is need for us to stay ahead of criminals. Recent intellect-driven solution is in advanced forensic investigation, such as lettered fingerprint detection or biosensor towards drug counterfeiting. Fluorescence organic inorganic nanohybrid materials, or IHN, are recently researched as suitable platforms for development of modern anti-counterfeiting material. The OIHN has unique properties due to its large surface-to-volume ratio, allowing more reactions to occur on their surfaces. It also has ease of synthesis and chemical modification, which provides versatile platform for many applications. POSS, polyhedral oligomeric silicosine, are a family of OIHN obtained from the hydrolysis of polycondensation of trichlorosilane monomers containing organic group. The properties include high chemical and thermal resistance, biocompatibility, luminescence, depending on the type of precursor that is being used. We also have development of POSS containing hybrid nanomaterial, leading to potential application as nanofiller for polymer matrix, catalyst, for adsorption, for sensor, and recently in public security. It's actually being utilized as barcode for anti-counterfeiting and confidential data encryption. POSS hybrid can be labeled by click chemistry, which is a set of chemical reactions that are fast, efficient, and highly selective. It's readily available for users, then uses no solvent or a solvent that is benign. It involves simple product isolation, no complicated isolation routine with no or minimal purification necessary. It has high yield. It is versatile and has a reliable conjugation chemistry for specific covalent cross-linking. Now, in the figure we have below, this is showing how click chemistry can be used in formation of hybrid POSS. We have our alkyne reacting with azide in the presence of a copper catalyst to give us our triazole. Metal oxide, for example, tungsten trioxide, has also been applied as photochromic nanoparticles due to their low toxicity, the strong local surface plasmodium resonance band. We have the photo absorption over a broad wavelength ranging in the near IR region of the electromagnetic spectrum. However, it is limited due to its weak color response and slow, occasionally irreversible photochromic behavior. The limitation has been reversed in few cases by introduction of semiconductors such as molybdenum oxide into tungsten oxide, resulting in a significant improvement in photochromic application and reversibility. The justification for this study. In recent years, there has been a growing interest in using click chemistry, to create novel molecular assembling material with unique properties such as high selectivity, sensitivity, and photostability. The lack of this unique quality in one entity has undermined the prolonged application of existing material in use for forensic and biomedical devices. It is in this regard that concerted researches have been made by synthesizing label POSS nanohybrid with unique properties that are not solely present in either the fluorescent entity or which is the POSS dyes or in the photochromic nanoparticle, in this case, which is the tungsten oxide, molybdenum oxide, and composite. When 3D POSS, with its ability to create highly specific and targeted material, is functionalized with tungsten oxide, molybdenum oxide, nanocomposite, which has unique optical and electrical properties. A new class of hybrid material that combines the unique property of both the POSS and tungsten oxide, molybdenum oxide, nanocomposite is created suitable for application, such as laser drug biosensing on anti-counterfeiting, which helps in fighting against criminal activities. So now the broad objective. The broad objective is to fabricate a functional nanohybrid material from click chemistry, labeled 3D POSS dyes and tungsten oxide, molybdenum oxide, and composite for anti-counterfeiting and biosensing. Methodology. The synthesis of labeled POSS in a click environment will follow these two schemes as illustrated in scheme 1 and 2. For the scheme 1, we start with the synthesis of POSS azide. This is synthesized by simply reacting POSS chloride with sodium azide. In other cases, we can actually use organic azide. However, in the course of this study, we use sodium azide, and we have a solvent DMF being used to get our POSS azide. The THF, which is a tetrahydrofuran, was actually used in dissolving after extraction of the desirable material from the solvent. We used it to dissolve the material and precipitate with methanol to get our azide. Now, the next scheme is the synthesis of pyrene labeled POSS. The synthesis here. No, you're on azide, please. Yes. Is the synthesis of the pyrene labeled POSS. For the pyrene labeled POSS, we have our synthesized POSS azide reacting with the desirable pyrene in the presence of copper 1 catalyst precisely, to give us our POSS pyrene. There was no need for further purification after this reaction has taken place. The reaction took place in a reflux environment and under nitrogen condition, and this gives us pure. We just need to do some washing using methanol. After dissolving in tetrahydrofuran, we had it precipitated also by methanol to give us a POSS purine, which was tested and is photochromic. Now, synthesis of tungsten oxide, molybdenum oxide, nanocomposite following scheme 3. This is our scheme 3. The first step is the preparation of the deep euthetic solvent, DES, and this was prepared by using choline chloride with ethylene glycol. Reaction of choline chloride and ethylene glycol and at 80 degrees Celsius led to this slide you are on is not where I am, please. The methodology. Okay. I think you're 2 slides or 3 slides away. So, no, not this place. Okay, so we have a choline chloride synthesized. Okay. Sorry. I'm on the 13th slide, please. Yes, after the synthesis, we have the doping. In this medium, we doped both the 3D POSS purine and the synthesized tungsten oxide, molybdenum oxide, and a composite into chitosan film. Chitosan slurry to form a film. Now the result. The molecular structure of PLP, which is the POSS labeled purine, and the tungsten oxide, molybdenum oxide, and the composite, and the newly formed film, nanohybrid film, were analyzed using FTIR spectroscopy. Please bear in mind that only FTIR reports will be discussed on this platform, as other characterizations are yet to be carried out. So we have from figure A and B, we have present a representative illustration of the interaction between PSS azide and the purine derivative with alkaline-like properties. It is evident that the azide group, the signal at 2050, that's 2050 per centimeter, it's actually disappeared after the POSS purine had been formed. And also we have a newly formed signal for carbon double bond of purine that emerged. Furthermore, the FTIR spectrum of the PLP has shown the presence of the silicon oxide silicon bond. Sorry, I cannot just be focusing on that. I couldn't be pointing to what I'm doing, and I'm saying that the pair, what I'm presenting is not what is displayed. Okay, so furthermore, the FTIR spectrum of the PLP in figure B reveals the presence of the Si bond signal, so within the range of 1,134 and 1,022 per centimeter, confirming that the T8 silicosine, its core remained unaffected by the reaction condition or the potent nucleophilic azide. So the presence of the distinct and prominent infrared band within the range of 400 to 1000 per centimeter, as depicted in figure D, is commonly associated with metal oxygen, stretching vibration, specifically the absorption bond at 436 per centimeter and 582 per centimeter and 624 per centimeter can actually be attributed to the various terminal bands of oxygen, tungsten, and oxygen bending, or WO bending. So we also have that of molybdenum and oxygen, and we have that of tungsten and oxygen, and we have that of molybdenum, oxygen, and tungsten stretching. Meanwhile, the band at 797 per centimeter, that of at 830 per centimeter and 891 per centimeter are linked to the oxygen tungsten oxygen stretching, the mode. Yeah. And also additionally, the absorption band at the absorption band at approximately 970 per centimeter and 141 per centimeter corresponds to the stretching of the molybdenum oxide bond and tungsten OH as indicated on the FTIR report. Now, for the, yes, we have this, we have the evidence of anti-counterfeiting being formed when what was checked under UV. When it was exposed to UV, we have a POSS purine test for purity using a thin layer chromatography, and on this we have a spot which signifies the purity of the substance that is being synthesized. And also, as shown here, we have our synthesized material. When exposed to UV, it glows. That's to show the presence of its fluorescence, to show the presence of fluorophore, and at the same time it absorbs light and gives and changes from blue, light blue to deep blue, as shown on the slide, from light blue to deep blue with time. The intensity of the blue becomes more, gains more intensity with time exposure. When tungsten oxide absorbs ultraviolet light, it undergoes electronic excitation, and then as it relaxes back to the ground stage, it emits light at a much longer wavelength, typically in the near IR. The photochromic property showed instant change in color from white to blue when exposed to UV light. The response is shown above, from 5 seconds to 10 minutes and above. And also in the next slide, yes. So also in the next slide, we have that being displayed as shown. So conclusively, in this research, we successfully developed an environmentally friendly nanohybrid and nanohybrid film with transparency, exhibiting excellent photostability and photoresponsive responsiveness. This film has a practical application in anti-counterfeiting detection. It's worth mentioning that this is a pioneering achievement combining fluorescence POSS purine, chitosan, and tungsten oxide molybdenum oxide nanocomposite to create a transparent nanohybrid film. This innovative material can actually be used to coat various surfaces, such as the window, we have the door, and other surfaces. When exposed to UV light, it reveals legible patterns suitable for fingerprinting visualized detection. It's important to highlight that this material is photostable and is exceptionally, the photostability of the material is exceptionally high, owing to its efficiency and the simultaneous photochromic reactivity and the bright fluorescence achieved through FRET, which we call the Foster type resonance energy. While our current research has not explored specific application in biosensing and tumor ablation, which is one of the intended application, these areas will be the focus of our future investigation. I want to express my profound appreciation to Dr. Fu, Professor Fu Guodong, that's my supervisor in China, which I look forward to meeting him soon, and also to Dr. Rosemary Adedokun, one of the researchers in the group, and also to Prof. Sherif Adewuyi and Prof. Enoch Dare, And also, I'm grateful to Dr. Lisa Allen. If she had not actually been there, I wouldn't have been able to present on this golden platform. I'm so grateful. Thank you so much. We have some of my references here, and to everyone listening, thanks and God bless. I'll be waiting for contribution to this,
Thank you,
please.
Dr. Shepra, for your presentation. So any questions from anyone? Okay, no questions then. Thank you once again for your presence and presentation.
Thank you.
Thank you. So as our next presenter is not online, we can go with the presentation from Dr. Swangwoo Wu from Ethiopian Technical University, Ethiopia. And the title of the talk is Improving the Fatigue Design of Mechanical Systems such as Refrigerator. Hello, Dr. Swangwoo. Are you ready with your presentation?
Hello, I'm ready.
Yes. Share your screen with us.
Yeah. Can you see my slide?
Yes, it is visible. You can make it a full screen and start presenting.
And is okay? Can I start?
Yes, you can start.
Yeah. If you have some problem, let me know.
Sure.
And this is. Thank you for your listen to my presentation. My name is Dr. Wu. Today I briefly introduce of the UV light methodology. This methodology will improve the design of the mechanical system. I will present the entitle as a present improving of the particular design of mechanical system such as a refrigerator. This is the mechanical system. There are typical three, and one is a heat engine, another one is a refrigerator.
Hello. I'm
Heat
sorry,
engine.
but the
Hello.
slide is not changing. We are on the first slide only.
Yeah. So, to the movie, eh?
Yeah, it's not moving.
Yes. Sure. Is it okay?
No, the screen is closed. Can you please share once again?
Yeah. Yes.
Yes, now we can see the second slide.
Yes.
Can you
This is a
can you
mechanical
please
system.
once try with another slide moving so that we can check whether it's working or not?
Yes. This is a movie.
No, we are still on the second slide.
How about? Do not moving?
No.
Yes, I don't know I don't know exactly this system that
Can you please share this slide to Lisa?
can I send the email?
Yeah, please send an email to Lisa. She will share that one, so that it will work perfect.
Yeah. I will find this Lisa email.
Yeah.
Lisa Allen. Yeah.
Yeah, Lisa Allen.
Yeah. Yes. And
Did you send the email to Lisa?
yeah, I'm attaching in the PowerPoint.
Okay. Um,
It takes
so,
1 minute, maybe, and maybe
okay.
the in my area that the internet speed is not much speed higher.
Yes. So, shall we wait for your presentation or can I proceed with the next one? Hello, Dr. Songwu.
Yeah.
So in the
I'm
meanwhile, shall
catching
I
on the
proceed with the
Wi-Fi
next?
and
Yeah, I will proceed with the next one so that you can send it to Lisa.
yeah, I will send it.
Yeah,
You
because
can
all are
proceed the next
waiting.
one.
Oh, okay, thank you. So in the meanwhile, like Dr. Songwu will send this
Thank you.
presentation to Lisa, we can proceed with the next one. And the talk is presented by Dr. Alice Mishenko from AA Galkin Dunstek Institute for Physics and Engineering, Ukraine. And the title of the talk is Electro-Optic Activity of a Non-Ideal One-Dimensional Photonic Structure. Hello, Dr. Alice. Yes, your screen is shared, but we cannot able to hear your voice. Hello, Dr. Alice. Your voice is not audible to us. So I think Dr. Alice is also having some issue with the microphone. As everyone is waiting, we can go to the presentation of Dr. Sarvesh Kumar Avinashi from University of Lucknow, India. Hello, Dr. Sarvesh.
Yes, ma'am.
Yeah, are you ready with your presentation?
Yeah, ma'am, I'm ready.
Yeah, sure. Thank you. So I'm going to make you the presenter. Yes. So can you please share your screen with us? Yes, we can see your presentation. You can make it a full screen.
Yeah, ma'am.
Please
Ma'am,
make it full screen.
okay, ma'am.
Perfect.
Excuse me,
Please
can you hear me now?
Presentation. So,
Can you hear
can I
me
start?
now?
Hello?
Yeah, please
Hello.
start the presentation. Yes, please start the presentation.
Okay, thank you. Uh, Good evening to all my colleagues and all participants in the 8th International Conference on Material Science and Engineering.
Can
This
you
is
please bit louder? Like your voice is not at all audible to us.
Okay, ma'am. Good evening to all my friends and all in 8th International Conference on Material Science and Engineering. Uh, my topic is morphology, mechanical and biological evolution of pure hydroxyapatite and its composite with titanium carbide for biomedical applications. And I am from University of Lucknow, India. My name is Shavesh Kumar Nashi. Uh, this is my plan of talk. Introduction, hydroxyapatite, titanium carbide and its application, synthesis, characterization. In characterization section, we investigate the XRD, same, team and biological compatibility, result in discussion. In conclusion, acknowledgement. Acknowledgement. Before starting the introduction of hydroxyapatite, uh, I want to tell that the bone is a vascularizing complex and hard tissue capable of self-healing, regenerating, and supporting the entire body throughout life. Bone defects are caused by infection, pathological wounds, accident trauma, and genetic disabilities. Uh, More than 2.5 billion bones defects are observed in India, and more than 70 million bone injuries occur worldwide annually. There are several sizes of the bone defect. The term critical size refers to the longer defects whether the bone is usual to heal, unable to heal spontaneously. The critical size defect can be healed by applying the bone grafting regeneration. Addressing the injured bone regeneration by this situation is a big challenge for clinical in bone grafting. Worldwide, bone is the tissues, most implant heart tissue. In this list, I can start our presentation and to uh, to to resolve this problem for the uh, injuries of the bone tissue. The hydroxyapatite is one of the best biomaterial that density is comparable to natural human bone or natural bone. Uh, Hydroxyapatite is the chemically similar to the mineral component of the bone and heart tissue in the mammals. HAP is one of the most important bioceramic materials for its unique bioactivity, and stability. It is the bioactive material. It promotes the bone in growth when used in the orthopedic, prosthetic, and dental implant. HAP does not break down under the physical condition stable in physical pH value. Uses include bone grafting, substitute, and coating on the metallic implant. The different nanostructures are also used as a smart drug vehicle carried in drug delivery application. The chemical structure, size, and shape of the HAP play a vital role to enhance its mechanical property and biomedical application. Here in this figure, we can see that uh, this is the bone fracture, and here the hydroxyapatite and other nanomaterials like metal oxides, polymers, and ceramics are are implanted on the scaffold. uh, then we can see that the in next sentence, this this size is the more than the critical size. The critical size, this means the critical defect uh, is in the range of the 1 to 2 centimeter. Then it can't be healed spontaneously, so we can applying the bone grafting to heal this. So we can say that clearly in this picture. And the application of this hydroxyapatite is many more. We can see that in figure A, this is the in hip implant. application, the femur heel. Here we can see the HAP coated cup. For making this cup, we use the HAP, and this cup is coated by the hydroxyapatite. Hydroxyapatite, that means the short form of the HAP. HAP is the short form of the hydroxyapatite coated femur seal. And we can see here the uh, many many application part. uh, Here we can see that the travel surface here is removed, and to make the plastic structure and HAP coated trivial components, and we implant. It means we can say that there are a lot of application in the bone implant application. And the next is continued. This is the porous hydroxyapatite eyeballs. This is main, and this is the lenses. And if we combine this, the artificial eyes is ready for ready to here for the surgery. Before surgery, we can see this, and after surgery, we can. And in this series, we use the hydroxyapatite coated in for the 10 dental implant applications. Here we can see that the real teeth, and this is the artificial teeth with HAP coated dental implants. HAP coated artificial dental implant you can see here, and after surgery we can see the clearly there is no looks like difference between the artificial and natural teeth. The titanium carbide, the titanium carbide received a significant attention because of its high elastic modulus, high viscous hardness, effective melting point, high density, adequate thermal conductivity, high flexural strength, high thermal shock resistance, and high resistance to corrosion. Titanium carbide Titanium carbide nanoparticles are the very stable and successfully utilized as the reinforcement agent into the composite due to their unique mechanical property and high thermal temperature stability. Here we can see the structure of titanium carbide. The titanium carbide is an extremely hard ceramic material with abscess structure, and uh, the titanium has the various attractive properties such as we can say before, and we go to the next slide, and I want to tell the application of the titanium carbide. There are many applications of the titanium carbide. You can see in the screen that electromagnetic shielding, microwave of energy transformation, microstructure enforcement, and strength and ductility enhancement. Here we use the titanium carbide to enhance the mechanical strength, that is compressive strength, tensile strength, yeah, three-point bonding strength of the hydroxyapatite. That's why we make the composite with titanium carbide and hydroxyapatite. This is the experimental techniques for the synthesis of pure hydroxyapatite. The synthesis method, there are three methods: dry method, wet method, and high temperature methods. In dry methods, we can say that the solid state reaction method, mechanochemical method, and the wet method with chemical precipitation method, uh, sonochemical method, hydrolysis, emulsion process, sol gel, hydrothermal treatment, microwave synthesis route. High temperature methods include uh, the conversion method, spray pyrolysis method. Go to the next slide, and here I am talking about the synthesis of pure hydroxyapatite by the wet chemical precipitation method. For the synthesis of hydroxyapatite, first of all we take the 1 mole solution of calcium nitrate tetrahydrate with distilled water, and 0.6 mole solution of disodium hydrogen phosphate dihydrate separately, and Both solutions were mixed gently to add with the help of magnetic stirrer at the hot plate and uh, mixed well with the help of magnetic stirrer hot plate. Then we add the NaOH pellet. Then we add NaOH pellet to maintain the pH up to 11 at the constant stirrer at the temperature 60 degree. And then when we maintain the pH at 11, then we get the white suspension of HAP, white suspension of HAP, or we can say the milky suspension. And after that, uh, thereafter, uh, we we store the white suspension of the HAP and dry it at the temperature 150 degrees Celsius for 2 hours. And further we can it powder form. Further it can make the powder and then calcite it at 1100 degree centigrade for 3 hours. Then we find the white uh, white material of the hydroxyapatite, and then we grinding for 3 hours with the help of mortar and pestle. Then we achieve the hydroxyapatite powder, and it is confirmed the hydroxyapatite powder. It was confirmed by the XRD. It was confirmed by the XRD. When we complete the synthesis of hydroxyapatite, then we make the HAP and TIC composite via solid state reaction method. In solid state reaction method, some points uh, which is shown in the screen, uh, we take the appropriate amount of HAP and TIC, mixing mixing and grinding in acetone media for 3 hours and drying. After drying, we make the pellet at 8 ton with the help of pelletization machine. Here, uh, we can see that the HAP pellet, uh, HAP pellet were HAP and HAP composite pellets were made by the pelletization machine. The sintering at after making the pellet, we sinter at 1200 degrees centigrade for 3 hours. 3 hours, then we got the sintered pellet. We got the sintered pellet, uh, which can that can see at the screen. After that, the characterization technique, we performed several characterization techniques on these pellets, like XRD, FTIR, Raman, STEM, EDX, STEM, mechanical, cell availability. These all characterization are performed on this sintered pellet. The characterization techniques are here, and in next slide resulting discussion. For the first, the XRD analysis. For the first, the XRD analysis. Here we in the XRD analysis we can see that here the XRD patterns of the XRD patterns of the fabricated pure hydroxyapatite and its composite are shown at the screen. Here the figure 1A shows the XRD pattern of the pure TIC, where we can say uh, and it was confirmed by the XRD, and it uh, uh, it was confirmed by the JCPDS number 00013 and 1400. Here the pure hydroxyapatite record pattern reveals the good conformity of the single phase formation of the hexagonal structure of pure HAP with lattice parameter A equals to B equals to 9.424 and 6.98, including the species group P63 by m. And and when we compare the composite, here we can say that the first composite in which the 5 percentage 5 weight percentage of TIC added in the pure HAP, and it compare then we it compare with the pure HAP and TIC, the high intensity peaks in these patterns were observed due to the HAP. The high intensity patterns are observed due to the HAP, and some of the low intensity peak, which are marked by the asterisks. Here we can see that the asterisk symbols here represent these are the represent the TIC, and the rest of the peak are the pure HAP. When we increase the weight percentage of TIC into pure HAP, we record the we record we record the lower intensity peak of the TIC were increases, right? Increases in further increasing the weight percentage of TIC into pure HAP. Here, the average crystalline size of the pure HAP in TIC were calculated and found to be 78.62, 78.62 and 22.84 nanometer respectively. As increasing the weight percentage of TIC into the HAP, the average crystalline size of the composite average crystalline size of the composite 95 HAP, 5 TIC, 90 HAP, 10 TIC, and 85 HAP, 15 TIC were found to be 76.13 nanometer, 68.8 nanometer, and 5.8 nanometer respectively, which show the decreasing trend of the composite sample due to the smaller crystalline size of the TIC. And next here the FTIR, and in FTIR we can clearly see that the bonding of uh, in hydroxyapatite, the chemical formula of the hydroxyapatite is C18P4 6 twice. So there we found here we found the vibration of phosphate in the broad range of, here we can see that in the all figures we can clearly see that in the all figures uh, POP symmetric bending, PU4 -3 symmetric bending are shown in the broad range, and here and sorry, and we can see the clearly in the high wavelength range the OH vibration was also occurred. In the Raman analysis, the highest Raman intensity peak appears at the at 693 centimeter inverse, which shows the symmetric stretching of the PO3 3 group during the formation of HAP. Here we can say that this is the symmetric stretching of phosphate group. UV visible spectroscopy. Uh, this figure represents the UV visible spectroscopy and the top plot of the pure HAP and its composites. Pure HAP and its composite. Here clearly in uh, this figure clearly shows that there is little absorption in the UV region, but in a visible region the plot becomes flat, which means that the synthesized composite might be used for the biomedical applications. The optical band gap the lies between these two. This here you can see that the energy band gap of the pure HAP is 3.96 electron volt, and when we add the 5% of TIC into pure HAP, it uh, uh, the band gap the band gap is reduces, or you can say that the band gap is decreases continuously decreases when we weight the weight percentage. When we increasing the weight percentage of DIC into pure HAP, the band gap is decreases. Here the same and edits analysis of the hydroxyapatite and its composites. In figure 5a, the same micrograph of the synthesis sample was shown, and here the same image of the pure HCP. Where HCP? There was a center at the 12 degree Celsius for 3 hours at the heating rate of 5 degree per minute, and this the reveals the well interconnected. This reveals the well interconnected the uniform morphology of the grain and grain boundaries. The well interconnected grain and grain boundaries. However, its high magnification. At the high magnification, here we can see that the sheen clearly show the well-developed surface morphology along with the random oriented porosity among the various grain of the HAP that is marked by the red dash line. This is the pores in irregular shapes. There is no any shapes. This is irregular shapes, and for the in the figure 5 C, D, E, and F, we can see that there is no max broad listing. This look like very similar. They look like the very similar, and after figure in the figure 5 G and H, we can see that the many senses as compared to the uh, figure A to F. In this, when we get the in the 15% of the TIC, then we observe that the tiny nanoparticle of TIC are nicely decorated, which is represented by the represented by the aqua colors at the high magnification only show. In the low magnification, uh, we cannot see the TIC, but at the high magnification it can be seen. Some of these nanograins were agglomerated on the surface of the large grain of the HEP, it marked by the dashed circles in the aqua. In EDX, next we can say that the elemental investigation of the synthesized pure HAP and its composed samples. It is stated from the EDX spectra that the field determined is associated with the existence of the various elements calcium, phosphate, oxygen, which confirm the synthesis of pure HEP. We can say that in the figure 6a, there is no any TIC elements are available. It means that this is the pure hydroxyapatite. And further, when we add the TIC, when we add the TIC into hydroxyapatite, then we you can see that here the some TIC elements are visible. This is the average EDX pattern of the hydroxyapatite and TIC composite. Further, we add the 10% of TIC into hydroxyapatite, then we can see at the different spot. At the first spot, we can see that here some TIC are available. Uh, that means the intensity of the TIC element is higher, and at the other point, we can see that the TIC is almost as comparable to the before. And further, when we add the 15% of TIC, we can found the similar uh, EDX pattern, similar EDX pattern. This is the term analysis, and here, here in the term analysis, we can microscopy has been required for the better understanding of the structure and morphology at the high resolution. Exploiting the mixed morphology, and this figure we can see that the figure A to C represent the mixed morphology of the composite, which indicates that the HAP and TIC have the merged completely. Further, uh, uh, Further, the selected area electron diffraction pattern has been utilized for the detailed structure of the fabricated nanocomposite. These SEAD patterns exhibit a crystal structure pattern, which indicates the polycrystalline structure due to the proper merging of the TIC into HAP atom, and the merged atom are creating a pair creating a parallel merge eating or creating the parallel diffraction pattern. At the high resolution transmission spectral microscopy, we can see here we can see here the spacing of the HAP were calculated, HAP and TIC were calculated. This is this team image and SED pattern and high resolution team is represented of the composite, not the pure HAP, it is the composite. And here we can see that the D spacing of the HAP is 0.273 nanometer, and D spacing of TIC is 0.217 nanometer respectively. The particle size analysis, uh, the particles at the hydrodynamic diameter of the synthesized sample, the pure hydroxyapatite in composite is composed of when we add the 5%, 10%, and 50% TIC into the pure HAP lies in the range of this. Here you can see that start from the 342 at the 342 and in at the 531. It means that the particle size of the pure HAP were a range of the range of the pure sorry for interruption. Uh, Here I want to say that the particle size of the pure HAP were ranges from 342 to 531 nanometer, and when and average particle size of the pure HAP is 459 nanometers. When we add the TIC 5% TIC into pure HAP, the range of the particle size increases. Here we can say that the 369 to 712 nanometer, and the average particle size of the composite is 531 nanometer. When we add the 10 weight% of TIC into pure HAP, this is increases, and we can see that the average particle size of the composites are 825 nanometer and 955 nanometers respectively. Here the mechanical behavior of the composites. Here we see that uh, this is the pure hydroxyapatite. Uh, here to measure the mechanical behavior of the sintered billet. This is the sintered billet, uh, which is kept in the which is measured by the universal testing machine. This is the image of before fracture, and this is the image of after fracture. When you perform this, the pure the compressive strength, this is the compressive strength of the pure HAP were recorded 141 megapascal of the pure HAP. When we increase the percentage of TIC, that is, we add the percent of TIC into pure HAP, the compressive strength become highest. And our composite here, the compressive strength of the 95 HAP and 5 TIC with the highest compressive strength as compared to the all composites, that is 186 megapascal. Further, here we can clearly see that where we further uh, increase the percentage of weight percentage of TIC into pure HAP, this is decreases. This means that we can say that uh, key for this percentage are very suitable for the bone implant application, because this it has the high compressive strength and load bearing capacity. In next slide, uh, we can see that this is the table. Yeah, this is the summarized table of the all data. Here the average crystallite size, grain size, average particle size, direct band gap, density. Here the green density means when before the center of the fillet we measure the density, this is known as the green density, and after after centering we measure the green density of the samples, or known as the center density. Here we see that the green density is less than the center density. In all composition, we can see that the green density is minimum, and the center density is higher in our composition. And the compressive strength, we can see in the previous slide, load bearing capacity is here, and the young modulus of the composite 95 HAP and 5 TIC has the highest, and the fracture toughness is the also highest. Therefore, we can use for the bone implant applications. Here, the most important part is that uh, mechanical performance or mechanical property of the composite 95 HAP and 5 TIC is the higher, but here we can see for the implant the biocompatibility characterization is the most part of the most characterization part before implanting the materials. So here we see that the LP activity for the pure HAP. This is the LP activity of the pure HAP. Activity of the pure HAP. is not higher, the ALP activity is not higher than the 95 HAP and 5 TIC. Here we can see that the 3 star, so it is very suitable compositions for the bone implant application. And the next biological testing here, the cell viability, that is MTTSA, the MTTSA, mhm, MTTSA. This is performed at the osteoblast cell of the topical area, and here we can we all see that at the different concentration has the different values. Here at the 10 microgram, this is the 2 star of the pure HAP, and this is the control. Here we get the 3 star at the 10 microgram. So this is the uh, it is the very suitable for this bone implant application. Here we say that the 95 HAP and 5 TIC is more suitable than pure hydroxyapatite because it has the bioactivity, is outstanding bioactivities, and also the mechanical behavior is excellent. This is the conclusion. In this study, the pure HAP is prepared successfully using the wet chemical precipitation method and HAP-TIC composite via solid-state reaction method. The particle size of the synthesized composite was found to be increased due to the particle of TIC occupying a position on the surface of the large grain of HAP. The concentration of TIC into pure HAP and sintering temperature have been optimized on the several mechanical parameters, namely density and modulus, flux toughness, and load capability. This study revealed that the HAP composite with 5 weight percentage of TIC substituted in the pure HAP has been maximum compressive strength, that is 186 megapascal, and fracture toughness is 9.82 megapascal meter per by 2. The composite having 5 weight percentage substitution of TIC showed the highest compressive strength, excellent osteogenesis, and cell viability, which may be used for the bone implant applications. These are the references. Uh, this work has been also published in the Ceramic International, in the Journal of Ceramic International, factor 5.2. I acknowledge the Science and Engineering Research Board, Department of Science and Technology, ST, New Delhi. I am thankful to my supervisor, Dr. C.R. Gautam, and my lab mates for their constant support. And I also acknowledge the Professor Atul Khanna, Department of Physics, Guru Nanak Dev University, Amritsar, India, for Raman measurement, and Department of Chemistry, and also acknowledge the Department of Chemistry, University of Lucknow, for the FDR facilities. Thank you. Thank you for the kind attention.
Thank you, Dr. Sarvesh, for your presentation. So any questions from anyone? Okay, no questions. So thank you once again for your presence and presentation.
Thank you. Thank you. Thank you so much, ma'am.
Yes. So we move on to next presentation by Dr. Alice Mishenko from Ukraine. Hello, Dr. Alice. Are you ready with your presentation?
Yeah, hello. Can you hear me?
Yes. So I'm going to make you the presenter. Yes. So can you please
Okay.
share your screen?
Okay. Can you hear? Can you see
Yes,
my
it's
screen?
perfect. Yeah. You can start your presentation by making it a full screen.
Okay. Uh, okay. So my name is Ales Mishenko. I will present the work of a group of Professor Rumyantsev. Uh, Professor Rumyantsev himself is on another meeting, so I will show his slides about our work. Uh, this work on photonics in general was started in about 2012 as a Ukrainian-Italian collaboration between Galkin Donetsk Institute of Physics and Engineering, Ukraine, and the Mediterranean Institute for Fundamental Physics, Italy. So, and here I will present a part of this work concerning optical activity in photonic crystals. So can you see the next slide? So if you have if slides are not changing, please let me know, because like in some of previous speakers, sometimes it's not changing. So this is my second slide. It tells a little bit about background of this work. So design and use of novel materials is a very demanding area of nowadays science. In particular, photonic crystals as structures that can manipulate light are in high demand for today industry. This includes so-called polaritonic crystals, uh, um, characterized by strong coupling between excitations in the crystal and the optical field itself, and simple photonic crystal where you can see light propagating through a crystal, changing his properties, which can be used for sensors, for another things, for many applications. So, okay, I can move right to this introduction. So, photonic crystals can be used in many different applications. For example, one-dimensional photonic crystals can be used in dielectric mirrors, which produce very high reflectivity at a specified wavelength. Two-dimensional photonic crystals can be used to produce photonic crystal fibers, which can make very high quality fiber optic communication. And for example, three-dimensional crystals can be used in the future in optical computers, and also could lead to more efficient photovoltaic cells, which produce energy with a very high effectiveness. And the optical computers, it's calculations that are made in using the light itself, using photons, which go from one um, um, uh, calculator, one integrated scheme to another, and calculate much faster within a much smaller volume than ordinary computers. So this presentation is about optical activity in photonic crystals. Optical activity is a special dispersion effect. Uh, and usually it is it appears due to peculiarities of structure of some medium, or due to optical activity of molecules of this medium. For example, some organic chemical molecules have their natural optical activity. In general, optical activity can be used to rotate the plane of polarized light. If we send a light which is polarized, for example, vertically to a medium having optical activity, then on the exit of this medium, the light will be polarized not vertically, but already rotated to some angle. And this can be used for also many different things, such as, for example, sensors, which very fast sensor, which use measurement of rotation of angle of this light to measure concentration of active substance in this medium, or structure of this medium, or any other things. What we do now in particular is studying the effect of electroaeration in a non-ideal one-dimensional photonic crystal, photonic superlattice with layer and defects. Okay. So electroaeration is appearance of optical activity due to presence of electric field. So we can manipulate optical activity by electric field, which is also very useful. And so the theory and what we have done. To study electroaeration, this means optical activity in a photonic crystal due to electric field. We start from construction of Hamiltonian of photonic crystal, 1D photonic crystal with electric field. So here you see this Hamiltonian, which is constructed from Hamiltonian of isolated molecule, Hamiltonian of dipole moment, meaning excitation of this molecule due to applied electric field, and operator of interaction between molecules, Coulomb force between molecules. Okay. We use the method of approximate secondary quantization, which means that instead of using a quantum wave function of a particles in terms of coordinate and momentum, we use a wave function in the terms of filling numbers of various states of the particle. So in quantum mechanics, we can have a limited number of states of the particles, and this filling number indicates how many particles are in each of these states. This representation just allows to uniformly describe systems with different numbers of particles. So what we want to do is to extract from all Hamiltonian the part of Hamiltonian which deals with excitation in this crystal. This excitation is represented in terms of quasi-particles, which are called excitons. each excitation is one particle exciton. So, and the excitation part of Hamiltonian and the wave function of the single molecule in the field of crystals can be found by solving this equation, where epsilon is energy of the molecule and phi is the wave function corresponding to a state of single molecule. Okay, so using secondary quantization, we have the following part of Hamiltonian, which corresponds to excitations, to these quasi-particles excitons. Here the operators denoted at the end of this equation 3 as B plus and B are operators of Born and disappearance of excitations, Born and disappearance of these quasi-particles. So what we need to do is to extract from these equations the measure of optical activity of this system. It's called rotational ability, and it's exactly the angle of rotation of polarized light in this medium. So the magnitude of this specific angle of rotation of the polarization light means that its angle of rotation divided by concentration divided by length. So it's specific to this medium and doesn't depend on the length of the medium and on the concentration of optically active molecules in it. So as from this equation, I will skip the mathematical formulation, which are a bit lengthy. But finally, so we arrive at the this expression for the specific rotational ability, consisting with two terms. With the term depending on electro-optical activity of molecules and the term depending on electric optical activity of excitons, meaning the excitations. So this is the main useful result that allows us to manipulate these two things differently. We can manipulate the concentration of active molecules, or we can manipulate excitations by electrical fields. So we arrive at the following results. So we are here interested mostly in the second term, which depends on excitons, on excitations in the photonic crystals. Having performed the following transitions, we can arrive at the results that can be plotted. These are the main results. The first figure, which is on the left, shows us the rotational ability in dependence of concentration. So we can see that using concentration, we can not only manipulate magnitude of rotational ability, but also manipulate the sign of rotational ability. That means that we can make photonic crystals to rotate light to the left or to the right. This means clockwise or counterclockwise. The second uh, picture shows the dependence on the excitation energy, on the energy of exciton, and on the parameter B of the equation that I showed earlier. Here we can see that we can manipulate the rotational ability of photonic crystals at a very high magnitudes, although because it's the angle is rather steep, it requires very fine tuning of this excitation energy. So in general, we can see that in this 1D theoretical photonic crystal, in which we remove some sublattices randomly by electro-optically active elements, by electro-optically active cells. We can construct the crystal which is able to rotate light and which is able to rotate light as we want by manipulating concentration and excitations from electric field. So this, as I mentioned, can be useful in creating electrosensors, which can tell us about the medium by the angle by which the light is rotated, and in general contribute in our understanding of photonic crystals, which have many applications, as I mentioned earlier. And most interesting is here is photonic crystal fibers and optical computers of the future. Okay, so if you have some questions, you can ask. And you can always send questions by email.
Thank you,
Okay.
Dr. Alice, for your presentation. So any questions from anyone? Okay, no questions, I think. So thank you for your presence and presentation.
Thank you.
Okay, so now we have the Dr. Songwoo presentation with us. So now we'll share that. And Dr. Songwoo, are you? Yes. So you can explain from there.
Yeah, yes. Can you turn on the share screen?
Yes,
Share?
yes, we're doing that. We're doing that.
Yes, yes, yes.
Yes. So whenever you need to change the slide, you can just let us know. We'll do that.
Yes. Thank you for listening to my presentation. My name is Dr. Wu. Today I briefly introduce of the UV light methodology. This methodology will be improve the design of the mechanical system. I will present the title as improve the particle design of mechanical system, such as a refrigerator. And this methodology improve the design of mechanical system. Next. Next. This is the typical previous. This is automobile. And you go past the previous. Yeah, yes. This is the typical mechanical system, and the one is the heat engine, another is refrigerator, and the heat engine is operating in the hot source and the cooling sink, and in the process the generating works. Another one is the refrigerator. Refrigerator is the moving the temperature from the low and the higher in the process, and the system is generating the works. Next. This is an automobile. Automobile consists of the engine, transmission, and drive, etc. Total component 20,000 pieces. Life target is between 10 years. To improve the performance and reduce cost of product design yearly. By live testing, engineers should be find the design fault of the product system. Next. This is airplane. Airplane consists of machine and door, aviation control, etc. Total component 200,000 pieces. Life target between 10 years. Next. This is a refrigerator. Refrigerator consists of the cabinet, door, interfixed, etc. Total component 2,000 pieces. Life target between 10 years. Next. This is a definition of the reliability. Reliability can define as ability item to perform required function under state, environment, and operating condition for the special period of time. Most of the mechanical system reliability, most of the reliability is yes, described as a best of, and the best of is if I follow the best of the product will be rejected from the marketplace because of the initial failure rate, higher failure rate, short lifetime. Because of that, many companies set up the life close plan as a design is improved. Best of previous and the changing to the straight line, and the product life that can be achieved without design failure. Next. This is a sinking picture of the RS Titanic in 1912. It came from the cold seawater British steel stop beside the Titanic struck iceberg. As a result, Titanic 200 people on board. It takes 2 hours 40 minutes sinking to drown deaths and more than 1,500 people. Next. This is disaster of challenge, and it came from the lucky boost sealed with true lava. As a result, this debacle occurred in 1986. All crew members lost their lives, and finally, American suffering and low esteem, and because this failure. Next. This is a Calypso point present. It came from the metal fatigue and the critic eye due to the lambda traffic load. As a result, at December 15, 1967, the Silver Calypso under the weight of the rush hour traffic. Next. This is a crash of the Highland Comet. This is the first commercial jet airline. It came from the structure failure, resulted from the metal fatigue in the airplane. Next. This is a failure mechanism and the new design. This is a structure. Structure subject to the repetitive load. There are some design flaw. The structure will be collapsed each lifetime. The issue, how to find the design flaw of the layer probability. The solution is reliable testing with under the Excel live testing. Next. Next, this is material to the. This is my the graphic study, the abstract, and I will first explain the quantum well model, and then transport phenomena in the process, and I will develop in time to failure model. To the developed Excel factor, I will the modeling and the system and the developing governing equation, and I will the define of the Excel factor. Finally, I will carry out the parameter alter with the sample size equation. In the process, I will find the design port. Next. This is a quantum well model, and this is the Schrödinger equation. From the boundary equation, you can find the Schrödinger equation solution. Next. This is a linear transport phenomena. J is a flux, X is the driving force, L is a transport coefficient. For example, and for the fixed diffusion, J is the material, X is the diffusion force, D is the diffusivity. Next. I will give you the one example of the diffusion phenomena. This is a solid diffusion in the impurity in silicon. It takes place electron migration induced voiding, buildup of the chlorine, and the traffic of the electric and the hole. And the junction function is described as sine hyperbolic and exponential. And this is a junction function. If I apply the electric field, junction function is distorted, easy to migrate in the left-hand side. And the next. Next. Please. This is the power port in the multiple system. Power is the define of the product of the effort and the flow. For example, and the for translated system is the effort is a flow, flow is a velocity, and most of stress is came from the effort. Acceleration factor is defined as the ratio of the effort and the temperature difference. Next. I will explain how to derive the sample size equation. Product follow the variable distribution. Life function is defined as a function of the shape parameter and the character's life. If I take a logarithm, we can find the Vx life. The issue how to define of the character's life. Character's life define of the testing data. Finally, and we can obtain the Vx life is a function of the chi-square function and the logarithm and the testing data. Next. To derive the sample size equation from the approximate Vx life, there are two approximations. One is a chi-square approximation, another is a lower approximation. Confidence level is 60%, R is less than 4, the chi-square function approaching R plus 1. Cumulative failure is less than 20%, lower function approaching X. If I rearrange it, we can find the sample size equation. Next. I will give you the one of the case of study. This is a redesigned compressor with a crankshaft. This is a refrigerator. This is a newly designed of the crankshaft in compressor. There are a lot of design parts in compressor. We don't know which parts. Compressor lifetime depends on pneumatic part. To find them, it requires the methodology. Next. This is a parameter design schematic. Compressor is designed to the increasing pressure from the low and the higher. We don't know how to use and the custom user condition and the environmental condition. Engine should be designed each part optimally. Life methodology consists of 3 parts: failure analysis, return product, parameter alter design modification, and the finally checking and the product achieve the life target. Next. This is a compressor in the vapor compression cycle. This is a vapor compression cycle. This is the piston. The compressor is a schematic diagram. Compressor operating by and the slide crank mechanism. Next. This is the product in field, and we finding and a lot of wear on the surface of the crankshaft due to the lubrication problem in field. It came from the improper design of the structure to modify and we reproducing patent art and collect them. Next. This is a load analysis for the X-ray testing. This is a vapor compression cycle. And from the conservation of the mass in complete tube, energy balance in the condenser, and the energy balance in complete tube, we can determine the mass flow rate, temperature of the evaporate, and the condenser temperature. Time to failure is dependent on the pressure difference and the temperature. Next. This is how to calculate the accelerate factor. Accelerate factor is dependent on the ratio of the pressure difference and the temperature difference. For worst of case, the pressure difference is 1.1. For accelerate testing, we increasing pressure difference almost 2, and accelerate factor is 3.4. For temperature, worst of case, the dome temperature is 19. For accelerate dome temperature 120, and the accelerate factor is 1.4. Total accelerate factor is 4.6. We apply and some duty cycle, we can search out design failure. Next. This is how to calculate the mission cycle. Life target of domestic compressor has a beyond life 10 years. Accelerate factor is 4.6. Total sample size of domestic compressor 100. Compressor life target for 10 years, almost 87,000 cycle. There is no problem in the 19,000 cycle. We can guarantee compressor life target beyond life 10 years. Next. This is the equipment used for the XLI testing. This is a test jigger. This is a schematic diagram. We can proceed the filament art with the equipment. Next. This is the result of the first filament art. Compressor locked due to the lubrication, 7 and 10,000 cycle. This is a filter photo. This is the result of the first filament art. We found a lot of wear on the surface of the compressor failure. And by filament art, we can reproduce the compressor failure in field. Next. We check the design of the compressor. We found three design problem. One is a low lubrication area. Another one is low starting RPM, and the compressor material problem. Next. As action plan, we modify and the compressor and the changing and the dimension, adding a new groove, and the changing material. By parameter art, we can collect the compressor failure. Next. This is a second result of the parameter art. Compressor wear is found in 19,000 cycle. It came from the interference between the crankshaft / water due to narrow clearance. This is old design. This is a new design, and we changed clearance from the wash and the crankshaft. By parameter art, we can modify and design part of the compressor. Next. This is a summary of the parameter art. There is no problem in the 19,000 cycle. In first parameter, we found a lubrication problem. And in second art, we found a wear problem on the surface of the crankshaft. In third art, there is no problem 19 and 20,000 cycle. Compressor achieved the life target beyond life 10 years. Next. This is another case of the study of the hinge kit system. This is a hinge kit system, and it consists of several parts: cover and the damper and the spring and the housing. There are a lot of parts of the hinge kit system. We don't know which part of us. Hinge kit life target depends on the from the design the flow of the part. To find them, it requires the life methodology. Next. This is a parameter design schematic. Hinge kit system is designed to close the door smoothly. We don't know how to use and the customer condition and the environment condition. Engineers should be design each part optimally. Life methodology consists of three parts: failure necessity return product, parameter art design modification, finally checking that the life target achieved. Next. This is the damaged product in field, and we found a lot of the crack on the surface of the hinge kit housing. It came from the fragile structure of the hinge kit system. By reproducing parameter art, we can collect them. Next. This is the load analysis for XLI testing. Hinge kit system is dependent on the door weight. To increasing and the impact, we adding additional weight on the end of the door weight. By controlling an impact, we can carry out the XLI testing. Next. This is how to calculate of the accelerated factor. Accelerated factor is dependent on the ratio of the impact. Worst of case impact is 1.1, and accelerated testing we increase the impact almost 2.7. Accelerated factor is 6.3. We apply and the duty cycle we can search out a design failure. Next. This is how to calculate the mission cycle. Life target of the hinge kit system is beyond life 10 years. Accelerated factor is 6.5. Total sample size is 6. Hinge kit life target is for 10 years, almost 36,000 cycle. There is no problem. 41,000 cycle. We can guarantee life target is a hinge kit system is beyond life 10 years. Next. This is equipment used for XLI testing. This is the hinge kit system. This is the test jig and the refrigerator and the controller. We can proceed the parameter art with the equipment. Next. This is the result of the first parameter art. Hinge kit house hinge kit system crack 7 and the 50,000 cycle. This is a field photo. This is the result of the first parameter art. By parameter art, and we can reproduce the design port of hinge kit system. Next. To reinforce of the fragile structure of the hinge kit housing system, we adding in some rounding outside, we adding in some rounding inside. We also keep it to reinforce the lid and the housing and the deck system. Next. This is another result of the first parameter art. We found in the leaked oil damp. It came from the ceiling structure. This is old design. This is new design. By parameter art, we can reproduce design the photo of the oil damp. Next. This is the second result of the parameter art. Housing covered hinge kit system correct 7 and 9,000 cycle. It came from the material problem. When operating and the operating and the hinge kit system, and damp spot is struck and hinge cover. Finally, and the hinge cover is the fracture. As an action plan, we modify material from to the plastic to aluminum die casting. By parameter, we can modify further housing cover of the hinge kit system. Next. This is a summary of the parameter art. There is no problem in the 41,000 cycle. In first parameter, we found in the fracture of the housing, leaked the oil damp. In second art, we found in the fracture of the housing cover. In third art, there is no problem, and the 41 and 74,000 cycle. Next. This is another case of the hinge at the parameter art. This is the row system. And this is a new design of the row system. It consists of the 3 parts. One is a rail, box, and spot. There are a lot of design parts in the rows. We don't know which part was. The represent lifetime depend on the parametric part. To find them, it requires the methodology. Next. This is a parametric design schematic. The row system is designed storing food in flashly. We don't know how to use it in the custom user condition, and then environment condition. Engine should be designed each part optimally. Derived methodology consists of 3 parts: failure and return product, parent art, design modification, finally checking and the product achieved life target. Next. This is a damaged product in field. We found a lot of the damaged product due to the design. It came from the improv design structure to modify and we can reproducing pyramid art and collect them. Next. This is load and export Excel testing. This is the pre-body diagram and the draw system. And by controlling and the food weight, we can carry out the accelerated testing. Next. This is how to calculate the accelerated factor. Accelerated factor is can be described as the ratio of the storing food. For worst of case, the food weight is 6 kilogram. For the accelerated testing, the food weight is almost 1.12. Accelerated factor is 4. We apply in the duty cycle. We can search out design failure. Next. This is how to calculate of the mission cycle. Life target of the DOA system. Draw system is beyond 10 years. Accelerated factor for the 4.0. Total sample size of the 6. Draw life target is for 10 is almost 36,000 cycle. There's no problem. The 37,000 cycle we can guarantee the life target beyond 10 years. Next. This is equipment used for the X-light testing. This is X-light art equipment and the controller. We can proceed the film art with equipment. Next. This is the result of the X-light loading in first filament art. Center spot is bent and the rail load is broken away. It came from the insufficient strength of the design flow. By pyramid art, we can reproduce a draw failure. Next. As action point, we design of the draw system for support center. We add in two additional reinforced leaf. For guideline, we excluding and low loss spot. By pyramid art, we can collect the draw failure. Next. This is the result of the first pyramid art. A box cover was broken and 3,000 cycle. This is a field photo. This is the result of the first pyramid art. By pyramid art, we can reproduce draw failure in field. Next. We checked and design of the draw system. We founding and the design defect and such as no corner and in high stress intersection area. As action point, we adding and some the loading and in the fillet, we thicken and reinforce the leaf. Next. This is the result of the second pyramid art. Compressor cleft and guide layer and we founding and sunken roller in 6,000 cycle. By pyramid art, we can the founding and design part of the draw. Next. As action point, we design a draw system for support center and we extrude the leaf. And for guide lane, we added in the backside leaf, we increasing and the fillet. By pyramid art, we collected the raw failure. Next. This is a summary of the pyramid art. There is no problem on the 30,000 cycle. In first pyramid, we founding and the box and the rail design problem. In second art, we founding and the support rail and the system is a design problem. In third art, there is no problem. Next. Conclusion. This is my paper and entitled as Improving Life Target of the Mechanical System during and establish the quantum transport life state and prototype and sample size. This paper is explained my background of the design theory. Next. 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 This is my books entitled the design of the life design of the mechanical system. These books explain of my background of design theory. These books also supplied a lot of the case of study, and it provided the design of the mechanical system. Next. This is my publication, and I published a lot of the paper in the international journal. Next. Thank you. Thank you for listening to my presentation. Hello. Do you have any question for my presentation? Hello.
Thank you, Dr. Songwoo, for your presentation. So any questions from anyone? Okay, no questions. I think thank you once again for your presence and presentation.
Thank you. Thank you.
Yes. So by this we came to end of our day 2 webinar, and we have successfully completed the 2 days webinar, and we are having successfully going on the second day conference in Paris, France, and it is still going on. And I thank you each and everyone for making this successful, and we'll let you know with the next dates of the conference through email, and the certificate will be sent to you right away, and hope we'll meet in the next event in the live. Thank you and have a nice day. And if you have any queries regarding this, you can write to the Lisa Allen, the program manager of this Material Science 2023. Thank you and have a nice day.
Thank you. Have a nice day.
Thank you.